Good evening, all. I welcome you all for the third day Atal Online 6-day Faculty Development Program on Navigation with Indian Constellation, Opportunities, Challenges, and Future Developments. Now, I request Dr. S.A. Arunmoli Madam to deliver the welcome address.
Good evening, all. I am very happy to introduce the resource person of this session. Dr. D. Venkata received the MTech degree in Radar and Microwave Engineering from the Department of Electronics and Communication Engineering, Andhra University, Visakhapatnam, India. He got PhD degree in Electronics and Communication Engineering from Jawaharlal Nehru Technological University, Hyderabad. His doctoral dissertation was conducted in consultation with Professor A.D. Sharma and examines the validity of ionospheric models for satellite-based augmentation navigation systems over India. He worked as a research assistant, junior research fellow, senior research fellow, and senior research assistant with the Research and Training Unit for Navigational Electronics, Osmania University, Hyderabad. He joined as an associate professor in the faculty of the Department of Electronics and Communication Engineering and is currently working as a professor, head research, Department of Electronics and Communication Engineering, and head of the Center for Atmospheric Sciences, KL University, Guntur, India. His research interests include satellites, navigational electronics, global navigational satellite systems, space science, and radio wave propagation. Dr. Ratnam was the recipient of the Young Scientist Award during the period 2012 to 2015 of the Department of Science and Technology, India, and the Research Award between 2015 to 2017 of the University Grants Commission, India, and Early Career Research Award between 2017 to 2020 from SERB. He has published more than 100 journal papers in IEEE, GRSL, and TGRS and JSTAR, and advances in space research, and 50 national and international conference papers. He has been awarded the Best Teacher and Researcher Award from KL University for several years in his service. He is a fellow of IEEE, IE, and Indian Remote Sensing Society, Union of Radio Science Professional Bodies. He has been serving as associate editor for IEEE Access Journal. With this brief introduction, it is evident that we are truly privileged to have such an accomplished expert with us today. We are confident that the insights and experience you bring will greatly enrich this session and benefit every participant here. It is indeed an honor to welcome you, sir, and we sincerely thank you for accepting our invitation to be the resource person for this FDP. Now, I invite you to share your knowledge and address the gathering, sir.
Thank you very much, ma'am. And
thank you, sir.
First of all, I'm very much thankful to be Dr. Mukesh sir for giving this opportunity. Is it my slides are visible?
Yes, sir. Yes, sir.
Okay. Yeah. So today the topic I would like to present the ionospheric corrections, which are essential for the satellite navigation systems. So my outline of the talk initially what we do at KL University at our Space Technology and Atmospheric Science Research Center, and a few basics about global navigation satellite system, GAGAN, GPS-aided geo-augmented navigation system, and navigation with Indian constellation, that is Indian regional navigation systems. And different ionospheric correction models we can classify as a single frequency ionospheric broadcasting models, which are meant for the low cost GNSS receivers, and how we can apply the machine learning models for the single frequency model, NEQ model. And also for the dual frequency models, we have developed the multi-frequency ionospheric correction models for Indian regional isolated TEC maps. And few results about extreme value theory application for the ionospheric TEC values and the ionospheric simulation and the routine modeling. So this is the plan of outline. So the Space Technology and Atmospheric Science lab at Yale University is established in 2012. So broadly, we investigate the total electronic content as well as wireless communication and the radio wave propagation. Dr. Satyanarayana sir is working on lower atmosphere and meteorological applications. And I have a colleague, Dr. M. Sridhar, works on global navigation satellite system ionospheric scintillations. Dr. Sampath Kumar is an expert in GNSS and ionosphere. So these are the research areas where we are working on it, how to improve the positional accuracy, that is a global navigation satellite system and the PNT, and the ionospheric radio wave propagation, and how the artificial intelligence and the machine learning models we can adapt for space weather modeling as well as the multipath. And also, other than the GNSS denied environment, can we have the 5G or the 6G can be used for the localization or a position estimation? And also the GNSS can be used for water vapor as well as the troposphere delay forecasting. And the quantum communication and the navigation systems also, we have been working on it. And we do the remote sensing data analysis in collaboration with the Center for Marine Fisheries. And we are trying to bring out open sea, cage, precision agriculture, and the digital twins. In addition to the space technology, we work on the atmospheric science by my colleague Dr. Satyanarayana on heat waves and the thunderstorm analysis, air pollution, and machine learning based weather forecasting and the cyclone tracking and the prediction, as well as a climate change and the global warming. So this is my team at here, Dr. Satyanarayana sir and Sridhar and Sampath Kumar Panda, and these people are working on various satellite navigation systems, 5G location-based systems, as well as in wireless communication. So these are the last 14 years I have been working on different funded projects from the funding agencies. So most of them are related to the how to improve the positional accuracy and with the ionospheric correction models right from the 2012 onwards. Presently, we have been working on traveling ionospheric disturbances and machine learning models for the NAVIC and the Gagan TEC for the project of ISRO. And also we have a recently 5G lab from the Department of Telecom, and we have been working on how positioning can be done with the data fusion and the deep learning with the 5G. So these are the projects we have ongoing, and the rest of the projects that we have completed on mostly on ionospheric simulations and the time delay as well as ionospheric correction models. So in our lab, we have the setup of experimental setup with the Indian NAVIC receiver, which captures the satellite signals from the NAVIC receiver. From the NAVIC satellites, the NAVIC receiver records the C by N naught and elevation and azimuthal angle and the pseudo ranges, ionospheric corrections, and the position information. We do for continuously monitoring the long range of the data. We are analyzing it. And so we have a software-defined radio GNSS receiver. The main purpose of this software-defined radio module to develop the scintillation mitigation algorithms. We can reconfigure the software in a GNSS receiver so that a mitigation strategies as a part of the GNSS receiver. We are trying out to modify the algorithms. How it is a robust from the ionospheric simulations, which degrades the positional accuracy. And the GPS Station 6 is a dual frequency or a multi-frequency GPS receiver, which records the ionospheric TEC as well as the simulations and the TEC rate. And we have a parallel computing system we use for weather forecasting, for a weekly bulletin of weather forecasting of temperature or the rainfall or the any alerts about the cyclones. We use this parallel computing system to generate to get the predictions using the weather research forecasting models, and we have some computers. And so this is the MET sensor meant for the GNSS water vapor estimation, which records the temperature, pressure, humidity. And we have a VLF receiver, very low frequency receiver, which is useful for detecting these shadow ionospheric disturbances. And as a part of the Tripura University, we have a Indian lightning detection network. So mainly thunderstorms and the lightning effects, we are going to analyze with the same kind of very low frequency receiver as a ILDN receiver. So let me introduce before going to the ionospheric corrections, which are essential for the transport applications or any aviation applications. We need high precision. So here the GPS, what we have the constellation has a 24 satellites, and the GLONASS also another set of 24 satellites from the Russian counterpart, and the Galileo. The satellites are maintained by the European Space Agency. So altogether, these more than 70 satellites are going to cater to get the position information. And these GPS satellites are situated at 20,000 kilometers. And the GLONASS is also around so, and the Galileo also. So all these satellites, we call it as a medium earth orbit satellites. So at any time, if 4 satellites should be visible, then we can calculate or we can estimate our own position without any reference on the earth. So that is the uniqueness. So how it is going to be done means there is a 2 ways. One is the satellite position, then another one is the range between the satellite and the ground. So here the ionospheric correction will take place where the positional accuracy degraded because of the medium of the layer between the 60 kilometers to the 2000 kilometers. So these ionospheric corrections we are essential, right? So here, so the position information, how we are going to capture based upon a multiple number of satellites are going to be deal with either code division multiple access technique, where the GPS works on the multi-user satellites will be taken as a code division multiple access techniques. But the GLONASS, they adopted frequency division multiple access techniques. And again, the Galileo, they adopted the binary offset carrier modulation techniques. So the user is always free signals are available from these a continuous transmission of the signals, which are transmitted by the GPS satellites as a waveforms are generated. Most of them are in BPSK modulation by the GPS, and the Galileo on the binary offset carrier modulations. So right. So even though all are in a different signal structure as well as the different digital modulations, but at the receiver, all constellations are compatible, and they work as a complementary to provide you, ensure you to estimate your position, the velocity in a better manner. So these are the constellations by the European Space Agency and Department of Defense of the USA and the Russians GLONASS. And so those in the previous slide, the 3 satellites are the global navigation satellite systems, right? So, but the Indian regional navigation system is a regional navigation system which caters only the Indian region and the surrounding the region. So the Indian regional navigation system is built in such a way that users anywhere in this region should able to acquire the service of a standard positioning service with a few 20 meters, and for the restricted users for the military purposes with a better accuracy, the service can be obtained by the Indian reference Indian regional navigation satellite systems. And there is a difference between the Galileo and GPS and GLONASS satellites. All satellites are the medium Earth orbit satellites, but the IRNS satellites are a geostationary and geo Earth orbit satellites. So here the altitude is varied at 36,000 kilometers, and they are going to have some of them, the geostationary satellites are moving along the equator, 3 satellites, and the geosynchronous satellites are 4 satellites are fixed in such a way that at any time, minimum 4 satellites are required to compute the user position. So, so this is how the constellation of the space segment of Indian Regional Navigation System is given here. These are the geostationary satellites that traverse along the equator. But here, geosynchronous satellites are situated here. They traverse in a figure of 8 manner. Then the entire service is going to be catered by the NAVIC system. So we have a NAVIC receiver installed at Keele University with the support from the Indian Space Research Organization, Space Application Center, and so they have provided us for the testing the NAVIC signals. And we are acquiring the data. So here in the top panel is showing the signal strength of each satellites received by NAVIC receiving antenna. So these are the dog values and dilution of the precision, how the geometry of the satellites useful for the position estimation. We are acquiring these observations continuously with a 1 second sampling rate. So this is how the dynamic space segment is a figure of 8 by the geosynchronous satellites, and the geostationary satellites are situated here, right? So this is the plan of our NAVIC constellation, so that a NAVIC positioning and the navigation and the timing services can be provided. So what is the major challenges when you're going to have the position estimation without any reference on the Earth by taking the satellite positions as a part of the navigation message, and the travel time between the satellite and the receiver we are going to measure as a transit time, and you can translate into the distances if you know the velocity of the light. Then the distance will contain some errors on 3 segments. One is a space segment, second one is a control segment, and the third one is user segment. So for if you are going to have only a single frequency model as a 1 sigma error, then a clock, the hardware itself, because when you're going to measure the travel time between the transmitter and the receiver, meaning that a standard satellite clock should be equipped by the satellites, and a standard receiving clock should be available in your receiver. Then the travel time we can able to measure. So the clock itself, the accuracies inducing the errors, maybe typically 3 meters, and the satellite perturbations, the satellite orbital corrections, which are in a medium Earth orbit satellites or a geostationary satellites, and because of the hardware of the satellites, also some 0.5 meters errors may happen. And the control segment, ephemeris error, and the 0.9 for the other parameters. And at the user, once the signal is received, then the signal has to pass through the medium between 20,000 kilometers from the satellite to the receiver. So here it has to travel and traverse through different atmospheric layers. Ionospheric layer offers you the delay as a 5 meters, and the tropospheric delay as a 1.5 meters, and the receiver hardware itself offers some noise as a 1.5, and the GPS receiver antenna, the surrounding geometry or the surrounding buildings or surrounding obstacles will act upon it as a multipath scenarios. Then altogether some pseudo ranges, the range error should be corrected. So here altogether there will be 8 meters on the each satellite. There is a changes are there. Then those errors should able to properly corrected or quantified. Then the user position can be enhanced. So here the SBOS, so the standalone GPS receiver cannot meet for high precision applications like a aircraft landing applications like the satellite-based augmentation system or a ground-based augmentation system. We can call it as a local area augmentation systems, which are meant for the high precision for the aircraft landing applications. So how you are going to model it? These errors, GNSS, we call it as GNSS errors. A proper modeling of these GNSS errors are very much needed. So you can look at here among all them, INSP delay is the predominant one. So we are trying to see how these INSP delays are not constant values. They are going to vary with respect to the day and the time and the location and the season and the solar cycle conditions and some space weather conditions also influence is there. So it is a dynamically changes, and the INSP delay is difficult to predict it. It is a very challenging, especially for the Indian region. So let us see how we are going to minimize from the 1.5 to the 0.2 meters by properly adapting the various kind of the models. So this is the a typical navigation requirements by the aviation. Let us say here, for example, the en route navigation. So the accuracy, we don't require much. Even 2 nano miles, nautical miles is enough. But when you have an approach or the landing applications, so 0.3 nautical miles accuracy is required. If you see for a single positioning service with a GPS, standalone GPS will give you the error up to 100 meters of the true position. Of course, we don't have a selective availability. We don't bother about this 25 meters. So then this 100 meters should be come down as a augmentation system by using a differential GPS or a wide area augmentation system or a ground-based augmentation system. So here in table 3, especially for the landing applications, normally we can categorize in a 3 categories. One is a category 1, 2, 3, where the decision height is varied from a 200 feet. Then the positional accuracy should be less than the 16.5 meters horizontally and the vertically 3.4 meters. So then we can rely on the positional accuracy of the GNSS sensor out. If not, then the pilot should depend on alternative navigation sensor. So when category 2 is nothing but when you're going to take the decision at 100 feet height level, it is very much critical, 6.5 meters and the 1.6 meters. If you look at the category 3 and the decision height is a 50 feet means almost zero visible conditions or a fog conditions. Even the GNSS, the positional accuracy you should rely means category 3 standards availability, right? So whatever the wide area augmentation system works only near category 1 decision height at the 200 feet. The wide area augmentation system fails for a category 2 or category 3 precision approach aircraft landing requirements. So in order to make the category 1 decision height at the 200 feet, that is the horizontal accuracy of 16.5 and the vertical is around 7.5 meters. So what are the operational augmentation systems? The first satellite-based augmentation system was developed by USA called as a wide area augmentation system. So all the airports are equipped by the wide area augmentation system in a USA, and in Europe it is called as a European navigation system. IGNOS caters the aircraft landing applications, and India we have our own satellite-based augmentation system, which is depends on the GPS signals as a Gagan GPS aided geo augmented navigation system. For the Japan's multi-satellite augmentation system, MSAS for the Japan. So let us try to understand why these ionospheric connections are more important for the Indian region as compared to the USA, because the USA comes under the mid latitudes and we are situated near the equator, and our entire the Earth is composed of a closed lines of the magnetic field lines. And because of the nature of the Earth's magnetic field variations, the ionospheric gradients are irregularities are more in Indian region as compared to the USA mid-latitude region, where these ionospheric irregularities are minimal. So then the positional accuracies also may not be that much deteriorated. So whatever the developed the satellite-based augmentation system at USA cannot be installed here in India for the aircraft landing applications. The reason is here the medium of the signals between the satellite and the receiver, the ionospheric irregularities are more, and it is very difficult to model it. So we need to make some adaptation and some modifications for the ionospheric modeling. So here let us see, for that one, the satellite based augmentation system contains a space segments of a GPS satellites, and this is the geo satellite is meant for providing the corrections to enhance the GPS positional accuracy. On the ground, we have Indian reference stations at various places across the India, and these Indian reference stations, which contains dual frequency GPS receivers and which provides a ionospheric monitoring information. And all this information is going to be sent to the Indian Master Control Station at Bangalore. So then at Bangalore, all stations data is going to be collected. Then the ionospheric corrections by adopting a models. Here at a 350 kilometers, we are assuming the ionospheric corrections. And these corrections are going to be sent to the user by a geostationary satellite. So what is the corrections are given here is going to be monitored at a grid point. We call it as ionospheric grid point. We are going to calculate this ionospheric grid point delay based on the IPP points, or the traversing points between the satellite and the receiver, which are going to be measured by the dual frequency receivers. So let us say here there is a 4 ionospheric delay information we are going to extract with the model. Then using this 4 information, and the user delay can be calculated. So this is how a ionospheric modeling or ionospheric corrections are continuously adapting. So this entire the process of corrections should be done within the less than the 6 minutes, because the ionospheric medium is going to be changed with respect to the time, day and the night, as well as the post-sunset conditions. So this is how, utilizing the ionospheric grid points information, we are going to extract, or we are going to calculate the user IPP delays. Then whether it is correct or not, we need to provide the integrity information. That we call it as a error bonds or confidence levels. So whatever the estimation you are going to make the differential corrections, and the integrated information is going to be provided by the geostationary satellite. So the ranging signal and the geostationary satellite will act as a GPS signal, like L1 and L2 signals are broadcasted for the positioning purpose. In addition to that one, a differential corrections and the integration information, which helps to improve the positional accuracy. So what are the how we are going to monitor the low latitude ionosphere? By the airports authority of India and Indian Space Research Organization, they have established the more than 26 GPS receivers, and they are continuously monitoring the low latitude ionosphere over the Indian region. All these locations. So the GPS receivers are installed, and the data is being continuously acquiring using these more than 26 GPS receivers as a network. And recently we have from the Survey of India also more than 900 GPS receivers data available for GNSS and the positioning applications, as well as for the monitoring of the ionosphere. So the Survey of India is now giving a free access of the data. So you can go through the Survey of India website for the details. So so let us see here. So how this low latitude phenomena is impact on our the global navigation satellite system. The biggest the problem is the equatorial ionization anomaly. So as we are above the northern hemisphere, above the equator, so then because of the magnetic field and the charged particles in the ionosphere, so there is a possibility of the drift as a E cross B drift, and the plasma every day will have a fountain effect, and the plasma is moving from the equator to the above and the below. And our so because of this anomalies, so there is a possibility of the uh, modeling errors. Sometimes it will have some interpolation of the modeling errors. So it impacts on the satellite-based augmentation system. So normally we assess or we evaluate the satellite-based augmentation system by 4 performance indicators called as availability, integrity, and continuity. These are the availability means sometimes the signal may not be available, and the integrity is going to be given the ensured the corrections you are giving whether it is correct or not. And so one more phenomena also is affecting the night time of the positional accuracy called as ionospheric scintillations, which are rapid fluctuations in the amplitude and the phase of GNS signals, sometimes a loss of log in the signal. Because of the loss of log for several minutes, so then the service is going to be interrupted. So that will impact on the continuity of the service about the satellite-based augmentation system, right? So these are the issues when you have the during the night time, these ionospheric scintillations, and the seasonally some equinox periods. So the more scintillations happens, and at that time the service may not be available for the few minutes. That also very critical for the aviation conditions. So we need to take care of how these ionospheric scintillations can be monitored, and how it can be forecasted, or how these ionospheric scintillation effects can be minimized in the GNSS receiver. That is one of the major research area which the researchers are working on it. So one more the phenomena called as plasma bubbles. So as we are near to the equatorial, so we have this ionospheric plasma is a continuous one, and it is dynamically varying. So because of these ionospheric plasma bubbles, the signals, the ionospheric delays will be more, and which is affecting the availability and the integrity. So this is the phenomena of equirelation anomaly. We have a E region and F region. So the electrodynamics, because the space which are contains the earth is moving with some gravitational forces are acting upon it. So you can see here it is an equator, and we have a electrodynamic process always pushes the ionospheric plasma in the left hand side and the right hand side. So when these ions are the free electrons are making as a electrodynamic process as a E cross B drift as a motor, and this plasma is going to be deported as a left hand side, and this is that it is happening daily, and which is a function of neutral wind, which is a function of external forces from the sun with the charge and particles. So this is a daily phenomenon is going to be happen at the at a low latitude region. So we need to take care of these corrections while you're going to incorporate for the PNT solution. So what are the ionospheric anomalies? Because it will act as a waveguide at the height of 60 to 2000 kilometers, which is a charged particles or a combination of the neutral particles. When the signal is traversing it, then you're able to monitor this plasma or these structures as a different scale sizes, right? So the irregularities are varies from 10 kilometers to the more than 10,000 kilometers. They are moving with respect to the time. Depends on the day and the night, sometimes eastward and sometimes westward. And the ionospheric corrections or the ionospheric TECs are varying with the two forces. One is from the space, that is a solar or a geometric storms, depends from the external side. And one more force is acting upon lower atmosphere from the stratosphere and the troposphere, right? So because of the stratosphere and the troposphere, so we can have a sporadic E or medium scale traveling and disturbances, which are going to be given a key indication about the earthquake related, the ionospheric signatures we can able to capture by using the MSTADs, which are pushed from the lower atmosphere. So when you're going to have the force is coming up from the sun, from the space as a solar or the geomastrons, we can have a large scale traveling ionospheric disturbances. So what we have discussed now, the equalization anomaly is a medium amplitude disturbances, and the red color is because of solar flares and the geomastrons. We can call it as a sudden enhancement density. And the plasma bubbles will have the large fluctuations, and the equalization anomaly and the ionospheric storms are medium scale, and the small scales are LSTADs, that is a traveling ionospheric disturbances, and the MSTADs. So we can able to monitor these ionospheric anomalies are creating a chaotic situation for the navigation and the communication systems, especially when you're going to operate in L band and S band. So how we can able to monitor these ionospheric anomalies? So we have a simple the parameter called as a total electronic content. Let us define. This is the GPS receiver or Indian reference receiver. Then I need to have the ionospheric correction, means the satellite is transmitting the signals on L1 and L2. Then the height of the ionospheric is 100 and the 1000 kilometers. Then the LRAD nest is varying, and this is the DE and maximum LRAD nest at 350 kilometers or the 400 kilometers. Then it is going to be reducing, right? So here I'm going to target at 350 kilometers. The ionosphere we are assuming here. Then how many number of the electrons contained in a 1 meter square area we are going to define as a total electronic content, right? So because when the signals are traversing along the irregularities, so then the signal structure or the signal waveform is going to undergo the radio wave propagation impacts of a refraction as well as the diffraction and the interference pattern. So when you have a refraction, we can able to measure this refraction in terms of the time delay as a total electronic content, which is directly proportional, whereas this diffraction we can analyze the sharp the changes in the phase and the amplitudes. So of course the satellite is moving, and the plasma drift also moving, and the receiver may be stationary or it is a moving, but still we can able to get the signals, and using the signals information, not only getting the position information, we can also monitor the ionospheric irregularities while moving the satellite, as well as the plasma also is a drifting, and under the various conditions of northern equatorialization anomaly. So in order to do that one, once you are going to define the total electronic content, that is how much delay is going to be experienced, that is proportional to the total electronic content from the satellite to the receiver, all the way from the 20,000 kilometers. So then I need to know at a maximum F2 layer, I assume as a 350 kilometers. So then the cutting point or the piercing the point, we call it as the ionospheric pierce point. So the location of the TEC or a vertical TEC, the corresponding the location we are going to estimate as a ionospheric pierce point, which helps us to get the ionospheric corrections. So for that one, we assume as the user is here and the center at center, and the ionosphere is at the 350 kilometers. Then we can compute the ionospheric pierce point along with the TS information, which helps us to cater a satellite-based augmentation system called as a Gagan system or any other augmentation navigation systems. So here, that is a time delay. Because of the ionosphere, we can able to compute based on the total electron content, which can measure by the L1 and L2 code and carrier phase measurements at the receiving end. Then using the code and carrier phase measurements, we can able to estimate the total electron content. Then if you know the velocity of the light and the frequency is nothing but L1 frequency or the L2 frequency, depends on the broadcasting frequency F, then we can calculate the time delay or ionospheric corrections. And the corresponding the ionospheric pierce point location as a latitude and the longitude, we can calculate based upon the elevation angle and the azimuthal angle of the GNSS satellite. If you know, then we can able to calculate the IPP latitude and the longitude. So these are the three parameters, how we are going to define the ionospheric pierce point latitude and the longitude locations and the corresponding the total electronic content. So this is how once we are going to have the ionospheric pierce point, then these ionospheric pierce points should be translated at the ionospheric grid points. So once these ionospheric grid points are known, then the user is anywhere in the cell, then the user can calculate or can enhance his position by knowing these 4 known IGP delays. So this is the working principle for satellite-based augmented system or Gagan system. So let us see at the Gagan system will works as a supported or aided by the GPS signals, and for that one we need a geostationary satellite. But when you have for a low frequency or low cost single frequency GNSS receivers, most of our mobiles are being used only a low cost GNSS receiver chips, which receives only L1 signals. When you're going to have a L1 and L2 is a little bit high expensive. So when you have only L1, then the positional accuracy is more. So what will be there for in our smartphones are a single frequency models for ionospheric corrections, because the ionospheric medium, because the ionosphere is a frequency dependent medium. So with a single frequency, we cannot measure accurately the ionospheric corrections. That is why the most of the GNSS, Galileo, you can call IRNSS or GLONASS, all satellites are a multi-satellite signals, are a dual or a multi-signals are generated by a coherent signals, because the fundamental frequency is the same. For example, the GPS, the fundamental frequency is a 10.23 megahertz. Then the L1 frequency is a 1 multiplier, 1575. And another one is another 127 multiplier. Then it is a 1227 megahertz. And these frequencies are differed, but their properties, coherent properties are the same, so that the ionospheric dispersive nature can be measured. So, but at the receiver, so we don't have a L1 and L2. So then in our receivers are equipped with the mostly on Klobuchar model. So Klobuchar model is a simple prediction model. And these ionospheric corrections are being transmitted by the satellites as a navigation message. Then the receiver data, navigation message, when you're going to decrypt it, so then we can acquire these Klobuchar coefficients. So we can predict the solution from the ionospheric corrections. So the positional accuracy is only 50% accurate, and nighttime it was given as an offset, and always the peak of the day is 14 hours. But if you look at the low latitude ionosphere, the daytime peak may not be 14 hours, sometimes 11 or the 12 or the 13 or the 14 hours. And during the night time, we have the ionospheric irregularities of plasma bubbles as well as the scintillations. So so the Klobuchar model is giving only a reasonable ionospheric delay corrections, which are received by the GPS navigation message. The any quick model is the official global ionospheric broadcast model from the European Space Agency, caters for Galileo satellites. So the Galileo satellites transmits the three coefficients, ionospheric coefficients, and using these three coefficients, the user can estimate the ionospheric corrections, which are built on the an empirical 3D ultra density model. And so there are several efforts are made how we can able to improve the Klobuchar model for Baidu navigation system. What they did is they have adopted the Taylor series expansion, and during the night time, rather than giving the offset values as a 5 nanoseconds, and they have modeled the nighttime variations. And to represent the better ionospheric information, they have gone for, rather than the 8 and 9 and 10 and 14 coefficients, they have adopted. And the model was improved around 65% model is better than the Klobuchar model. And recently, the Chinese navigation system, the Baidu navigation system, they have come up with their own navigation ionospheric delay correction model. We call it as a BD global ionospheric map, which is built on the spherical harmonics function model, and it is working reasonably well in even low latitude ionosphere. And also one more NTCMGL model, which is now officially translating from the NEGIC model to the European Space Agency. Now the official model is NTCM model, which works on the solar radio flux, and it requires some 12 coefficients. And also some of the researchers, they have adapted the Klobuchar coefficients. So they have classified, rather than giving a entire 370 sets for 370 days for a year. So they have given a separate 370 sets for low latitude regions and mid latitude regions and high latitude regions. So here it is not height, it is a high latitude region. So we have made some attempts how these single frequency ionospheric correction models we can adapt it. So we have tried with the spherical harmonics function model, and considering the 14 GPS receivers data, then we have adapted the spherical harmonics function model, and it is reasonably better accuracy of the RMSE when you are going to compare with Klobuchar and the NEQUIC model. And also we have tried with, rather than the single shell, we have tried with the multi-shell spherical harmonics function model Klobuchar. And we have tried with ARMA model along with Kalman filter. And these are the some of the attempts that we have made. And NEQUIC model also is over the Indian region. It is capturing the equatorial anomaly better than the Klobuchar model. And a machine learning model also we have implemented with the NEQUIC model. Let us see how we have implemented the machine learning model for improving the NEQUIC model. So before that one, how these models we can able to analyze. For example, NEQUIC model, the 3 ionospheric coefficients are a Klobuchar 8 coefficients. You can acquire from this website. And also the BD game coefficients also we can acquire from here. And some of the data sources, the global ionospheric maps data we can able to acquire. And whether the solar or the space weather conditions we can able to test with the geomagnetic indices, DST and the KP indexes. And the GPS receivers as a part of the IG stations, we can acquire freely the GNSS Linux data. And we can analyze this positional accuracy with the help of open source tool, GLab data processing. We have analyzed it with the Bangalore station. And we'll see how we have analyzed these models over the 2022 to 24 with respect to the different ionospheric conditions as a quiet as well as the disturbance based on the index values. So normally, because of these geomagnetic storms or the geomagnetic activity, the coronal mass ejections are erupting from the sun, are moving towards the Earth's surface, and the plasma also impact or the influences will be there. So these we are going to measure with the help of the KP or the DST index values. And so we can able to calculate using the simple the coefficients of transmitted by the navigation message. This is the the Chinese BD GIM model, and this is the global ionospheric map and the Klobuchar map and Anyquick model. So you can look at here, the Klobuchar model works always at the 14 hours is the peak values. And during the night time, there is a straight line is indicating the 5 nanoseconds. So that is why the Klobuchar model is not able to work properly. But when you're going to have the Anyquick model formulation, which is done on empirical LRNST profiles of Anyquick formulation by the European Space Agency. So then you're going to represent the day-to-day variations for the year from 2022 to 24. For Bangalore station, we have analyzed the different seasons, how the model is working on it, and what we got is the PD GIM model is giving a better performance on both quiet and the disturbed conditions as compared to the Anyquick model and the Klobuchar models. And this is the vertical delays, ionospheric corrections for BD GIM and USRG and the Anyquick model and the Klobuchar model, and it is given as during the equalization anomaly entry and during the transition of this northern equalization anomaly, because of we are situated near the equator and the plasma is drifting towards the northern side as a northern equatorial anomaly and the southern side as a southern equalization anomaly. So this plasma values are giving a maximum peak values during the daytime, and so these should be taken care. So you can look at here as compared to the USRG and the Anyquick model is captured these EAA phenomena features very well as compared to the Klobuchar model. And the difference between these ionospheric corrections, you can see here the most of the larger difference values are can be seen with the Klobuchar model, and the minimum values can be seen at BDGM model. So over the Indian region, the BDGM model is performing in a better way as compared to the other two models. So this is how we have analyzed the performance of the BDE model or the ionospheric correction models, Anyquick model and the Klobuchar model. So here the USRG model as a reference model, and closely the correlation coefficients are coming as a BDE model, and so the Klobuchar model is giving you large errors. So we have so once this what is the relation between the ionospheric corrections and the position information? So whatever the corrections that we have given in the range domain, and this range domain should translate into the position domain. So then the range corrections will be translated into the position domain. For example, you have a 1 tech unit is a change. So then there is a change in the positioning error will be a 0.4 meters. So let us try to understand. So these are the locations of the GPS receivers. We acquire freely the data. So you can also acquire the data from these stations, and you can also implement for these locations, IISc and Hyderabad and Lucknow. And these data we have obtained the dual frequency GPS model, and we have compared with the all the stations. Then what is the performance which is coming to the closer to the dual frequency model. So this is the analysis we have carried out for different stations, right from Hyderabad and Shillong and the IIT Kanpur and the Lucknow, Dehradun, and Port Blair. So these Rhinex files we have processed with the GLab software, and the Rhinex navigation file, which gives you the information about the satellite position information. And regarding the range information as the carrier phase and the code phase information is going to be, we can acquire with the help of the Rhinex observation files. And these two are the input for the GLab tool. Then if you, so you can choose the standard positioning service as a mode. So then the positioning errors we can able to calculate as a 3-dimensional northern and the eastern and the up. So if you are going to change the model, then you can see there is a change in the positioning error in a north, east, and up. So you can look at here, the up error is a most sensitive, and it is giving a larger values as compared to the east and the north errors. So here it is given as the statistics, how the BDK model is closer to the USRG model. As we already it was given in the previous slides, the BDM model, the accuracy is giving a better than the other models. So this is the bidirectional model. It shows the highest superior accuracy for the Ionospheric TEC estimation. So we are trying to now what we are working on in to how to improve these models, especially for geometric storm conditions in a real time. And we are working on how the machine learning models we can adapt for the ionospheric corrections for the various space weather conditions. So for that one, we have tried one attempt how to improve the NEPIC model, which is a standard model as a part of our smartphones or the low-cost GNSS receiver chips. So what we tried here is we want to augment the NEPIC model with the support of ML model. So this one, the idea was given here is the ML model is here, and the ML model we are going to enhance it with the help of the global ionospheric maps data is available from the international GNSS network, IGS network, and using this information and the difference between the NEPIC model and the code model, we want to derive the residual difference between these two values as a uncertainty and the influential features of ML model as a solar activity, which indicates the F10.7, which tells us about the solar radiation, which is a direct proxy of influence of the ionospheric corrections. 70% of the change is responsible from the F10.7. And also, we have given the geomagnetic activity because of the coronal mass ejections or the geometrically disturbed conditions is indicating the parameters DST, KP, and the AP indices as a features. Then we fed to the support vector regression model as a multi-input features as a day, hour, minute, and F10.7 and R, and the geometrical activities, DST and the KP and the AP. Then we are trying to, the target is nothing but the residuals of the vertical TEC rather than the actual vertical TEC values. So here at the single frequency, so this is the process is going to be done as a ML model is going to give you by learning the features from the difference of the code given vertical TEC and the NEQ vertical TEC data. So using this one, we can able to predict the differences of the vertical residuals. So at the receiver, our phone or the low-cost receivers directly outputs the NEQ model corrections. So these corrections are going to be augmented with the help of this entire ML module. So then we can have the improved version called as ML aided NEQ G model. And we have evaluated the model. So in this way, without modification on the NEQ model, the same model accuracy is going to be enhanced by establishing the residuals of the time series, which is derived from the help of aided of global ionospheric maps along with the NEQ vertical TEC time series. We can able to estimate or the improve the ML models. This is the approach we have adopted to improve the ionospheric corrections. So here it is given as a left hand, the features as AP index or the KP index. Whenever there is a sharp fluctuations, we can call it as the disturbed conditions. So here the DST index also is indicating here is a disturbed conditions. So we have considered one day as a disturbed day, which are having the highest DST values. And F10.7 is meant for the solar activity. Even sunspot number also is indicating the solar activity features. And these three panels are indicating the geometric features. Then we have generated or we have calculated the vertical TEC for the 24 hours for the complete 1 year for a particular location. Then we have given as a training period and the test period, and then we have analyzed whether the model is working or not with the improved model. So this is a typical the output of ML aided model for the entire global model we have adopted. And at a 0 hours and the 4 hours and the 8 hours and the 12 hours, you can see here the movement is going to be going left hand side to the right hand side. So always there is this is the northern equatorial anomaly, this is the southern equatorial anomaly. So as the UTs are changing, so then it is going to be moved from left to right hand side. So here clearly the improved ML aided model is capturing the equatorial anomalies for both quiet days as well as the disturbed days. So this is the so we have tested this model, the improved NEQ model, and we have also adapted rather than the support vector regression, and we have tried with the a simple neural networks model also, and we have compared with the code game model, and even in both low latitude as well as mid latitudes and the high latitude regions, the ML aided NEQ model, the performance is better, is indicating as a RMS error of about 2.98 meters. Or tech events. So these are the ionospheric corrections. That is a single frequency corrections, which are very helpful for single frequency users or the low cost users to enhance the positional accuracy. From a 1,000 meters or the more than 100 meters, it can be come down as an alternative solution at the user end. So most of these applications are meant for at the space at a user segment or at the user level. So we have tried here as these ionospheric corrections. Why can't we use these ionospheric corrections from the other sources? So these ionospheric corrections or the ionospheric monitoring can be done in a various ways. So the ionospheric monitoring can be done by the radars or by the air glows or by the other satellite data. So multi different ground-based observations and some radio occultation data also. So we have a multi-data sources, ionospheric data sources. Then how we can able to precisely model the Indian low latitude ionosphere. So we have tried as a data assimilation model with a Kalman filter. So let us see how this ionospheric correction model better than the single frequency ionospheric correction models we have implemented. So we have considered here the Gagan stations, which are dual frequency receivers. Then we have calculated the ionospheric pierce point and the corresponding the TEC values. So here it is giving as a Gagan, as well as we are combining the radio occultation from the cosmic, and also we can have other sources from the JASON altimeter satellites and the Swarm satellites also. So we have considered these ionospheric delay information at these points are utilized for developing the ionospheric correction model. So we have considered as a background model as a simulation model from the global ionospheric map and the GPS aided navigation system, that is a 26 GPS receivers data. Then we have obtained the TEC estimation, and we have considered the HF the ionosphere stations, that is the ground based ionospheric monitoring data, and the cosmic RO data. So the nature of ionosphere data is different, and the cosmic RO data is different, and the Gagan data is different. So all these ionospheric information should be in a uniform scale. So then we can able to adapt the assimilation model with the help of a Kalman filter. So what we did is here we have implemented a Kalman filter to have a data fusion algorithm with multiple data sources Then we have formulated as a measurement observations as well as a state vectors. So then we can able to predict by using the background measurement error covariance matrix. So this is the key factor, a properly choosing a background measurement error covariance matrix and the initial values. So we have obtained the Kalman filter output. We call it as a simulated Indian regional TEC maps. So using the GPS data, so we have considered the three instances where the equation anomaly is moving as an entry or in the middle or the leaving. So our daytime. So this is the night time because the UTC is given here, and for the converting into the Indian local time is a 5.5 hours. So the Iravat model, that is the estimated regional ionospheric vertical DEC model, is capturing the equation anomaly features very well for both quiet and the disturbed conditions. So this information we can utilize for the Gagan or for providing the ionospheric corrections. So this is the how the equation anomaly we can see at a one longitude at a time is varying. So here it is given as a equation anomaly, and so this is the equation anomaly because of the plasma is acted as a fountain effect of E cross B drift from the equator, and the plasma is departed into the mid latitudes of about 10 degrees to 15 degrees. So then during the disturbed day, you can see here as compared to the quiet day. So the daily phenomena of the equation anomaly is expanded towards the 40 degrees of the latitude. That is a polar words. So you can clearly see there is a change in the quiet day and the disturbed day, and the model should be able to capture this kind of the AEIA, a regular EIA, well-formed EIA, or a enhanced or the depleted EIA, depends on the geometric conditions. The model should be able to capture. So then the ionospheric corrections can be done in a proper way. So this is the model we have tried with the different conditions, and we have changed the background model rather than the code global ionospheric map. We have tried with the ionospheric reference model as the initial model, and these are the data sources we have fused, and we have adapted the background model level covariance as well as some ensemble and the multi covariate analysis. And we have compared these EIA phenomena for several during the geometric storm occurred in the last solar cycle, which is a severe one at March 17th, 2015. So here is clearly capturing the equation anomaly as compared to the other models. So these are the IRI model is a background model we have chosen, but these are the models we have compared with the other centers processed JPL from the NASA process data we have utilized. So other center, Europeans, and the continuous operating system maps. So this is how we have developed the Indian regional maps, Airavati maps, to cater the ionospheric corrections. We have compared with the Indian IGS locations, Hyderabad and IISc and the Lucknow also. So there is a much improvement with the IRI with localization as compared to the other models. So then this traditional Kalman filter model, so we have implemented with the machine learning model, deep learning model. We call it as a bidirectional long and short-term memory model. We have adapted the same IPP points and the Gagan stations, and we have applied the BiLSTM model. Then we have tested for the geometrically quiet day and the disturbed day, as we did for geometric storm conditions for the estimated maps. So here the BiLSTM model we have compared with the basic model, adjusted spherical harmonics function model, and these are the models are the performance is not better as compared to the bidirectional LSTM models. So this is the single frequency models we have discussed for the low cost GNSS users. Then dual frequency models, which are meant for the high precision for the decision category applications, high precision aircraft planning applications. So we can adopt the machine learning models as well as the Kalman filters here. So and also we have made an attempt how these the ionospheric irregularities sometimes will have extreme TEC values. So then there is a threatening for the satellite navigation systems. So then the International Civil Aviation Organization already they have mandated that the GNSS is a primary navigation tool for the civil aviation. So what is the worst values are the extreme TEC values can happen. So then accordingly the risk management can be done, right? But whereas the International Civil Aviation Organization, they have provided the service thresholds at 125 tech units for the quiet conditions and 175 tech units for the disturbed conditions. But sometimes these values are changing because sometimes the report says more than 200 tech units also is indicated because of the solar flares and the geometric storms. So we want to analyze a long-term data for risk assessment, how these extreme values can be analyzed. Because these are the rare events, we cannot apply the probability distribution function where the central limit theorem, which depends on the mean values. So when you're going to have a mean values, then it is difficult to have a extreme values. So that is why we have gone for the generalized extreme value theory, which is different from the normal probability distribution functions, where it works on the central limit theorem at mean values. We have adapted the uh, uh, a generalized extreme value theory to get the extreme ionospheric TEC values, how we can able to analyze. So for this one, we have considered more than 25 years data of 8,000 GNSS receivers data. And we are trying to understand what is the maximum threshold of a quiet conditions and the disturbed conditions so that the user can be alerted. So these thresholds we want to define by properly analyzing the 25 years data of 8,000 GPS receivers data. So we have done various kinds of the data pre-processing as a outliers and the artifacts and we have removed, and we have applied the a generalized extreme value theory. So as I said, it works on the tail distribution rather than the main values. So here we are going to understand the tails of the estimated distributions so that the extreme values can be we can able to derive with the help of the GEV distribution, which is indicated as a shape parameter and the scale and the location parameters. So this is how depends on the data set, whether it is fitting the Campbell or a Frischel or a Weibull. So we can choose then the extreme TEC values, we can able to obtain it. So we have defined for our Indian region, what is the extreme values for Japan, low and mid latitude regions, as well as the global region. We have analyzed with the help of this GPD analysis. So these are the total electronic content for the 25 years for a quiet conditions and the disturbed conditions. Look at here, there is a lot of values are moving more than 200 tech units, right? So these are the rare phenomena we are going to analyze so that in the future there is a possibility of the extreme values or not. We have analyzed as a 11 years or the 22 years or the 44 or the 66 years. These are indicating means in 11 years there is a possibility of a 131 tech units may happen several times. It's not in a one time. So this is the analysis is normally they do for earthquake analysis. Earthquakes are rare events and they have a very limited events. So then there is a possibility of the earthquakes. Prediction can be done efficiently by the extreme value theory. The same theory we have adapted for understanding the extreme TEC values for the ionospheric TEC, and we have defined the thresholds for the global as well as the Indian region here. So this is the we have defined as for the moderate conditions, a 121 tachyons are exceeding. So then we can indicate it as a moderated the ionospheric information. And if it is exceeding the 131 tachyons, and if you compare to here in Japan, the thresholds are varying. And for the global, the global 139 and the 159. But whereas the ICAO is was given as 125 and the 175. So these are the global threshold levels we have defined with the properly adopting the extreme value theory. We have adopted both extreme value theory at the maximum values and general Pareto distribution functions. So, and also we have tried this extreme value theory with machine learning approach also. So this is the GeoNet data, and we have adapted the GPD analysis. And the shape parameter and the scale parameters we have translated as a machine learning problem. And we have adapted the light GPM as a features, as a diurnal variations and the GPT, and peak of threshold, maximum TEC and the DST, and MG2, which is F10.7 equivalent solar activity index parameter. So then we have predicted the TEC values, and again these predicted TEC values are applied for the extreme value theory, GPD theory. Then we have refined further the return periods, and we have recommended the thresholds as compared to the GPD analysis. So these are the for example, if you see the 2024, there is a geometry storm, and you can see here a large of the extreme TEC values are occurred during the 10th May, and this analysis we have done up to 2022, and so it is exceeding the more than 175 tech units. So this is the we have given the recommended the return levels for Indian region and the Japan and the global region. So one more aspect of ionospheric corrections and the ionospheric irregularities is the ionospheric scintillations and the plasma bubbles. So the ionospheric scintillations can be quantified with the help of scintillation index, that is a S4. Then the S4 value varies from 0 to 1.414. And the rho T is indicating as a rate of change of total electronic content of the TEC. And the C by N naught, which is a function of S4. And the S4 can be derived by the root mean square value from the carrier to noise ratio from the GPS receiver. And these are the solar and the geometry parameters. And so the Ionospheric is giving you the equatorial spread of indicating the plasma bubbles. So in order to monitor the ionospheric irregularities of ionospheric scintillations or the plasma bubbles, so we need to have the two important parameters. One is the ionospheric S4, another one is the rho T parameter. So we have derived the S4 using the GPS receiver, and we have compared this GPS receiver from the software defined radio, and we have compared with the we have a GPS receiver at the Novotel, and so you can look at here the whenever this is the situation is happening, then the loss of the log signal may happen. Okay, so I'm stopping here, and so these are the few results about the ionospheric modeling or the ionospheric corrections or the modeling efforts what we did. Any questions? I'm happy to answer. So most of these results are prepared or worked by my past and the present PhD scholars and the postgraduate MTech students and BTech undergraduate students for their research contributions. Any questions?
Good evening, sir.
Yeah, good evening.
Sir, this cosmic RO data and ionosphere station data can be obtained over India freely, sir?
Yeah, cosmic data and
It's ionosphere.
Ionospheric data is not available on the web. We have obtained from the Tata Institute of Fundamental Research Berlin facility. We can acquire the Ionospheric data from the Tata Institute of the Fundamental Research, and some ionospheres are available with the ISRO and Indian Institute of Geomagnetism, and the cosmic RO data over the Indian region, the trajectory we can acquire from the web.
The NASA website, sir?
Website, cosmic website is available in that one, and also you can have these swarm satellites as well as and JASON altimeter satellites also giving you the total electronic content.
Okay, sir.
So these are the radio occultation based GNSS observations. So we can acquire over the Indian region. It depends on the crossover of the satellite pass.
Sir, and also, sir, the last thing is, could you please tell us some of the recent research potential topics, because a lot of research scholars are attending, so that will ignite them to do the research. Some potential research topics, kindly let us know, sir.
Yeah, the research, the problems you can handle because, as I said, as we are in the low latitude region, so these are the ionospheric irregularities, how this equidistant anomaly impact on the GNSS positional accuracy. We can analyze with the help of a machine learning models. So you can that is the one way we can able to study the equation anomaly phenomena modeling or the TEC modeling we can able to do with the help of a machine learning models. Another aspect is how this lower atmosphere is coupling and pushing the total electronic content variations, which are very important for ionospheric seismic and the earthquakes or the tsunami studies. So these are resulted because of the atmospheric gravity waves are propagating from the earth, and because of the epicenter variations are translated as atmospheric gravity waves and pushing into the total electron content as a form of a traveling ionospheric disturbances. So these how a coupling process between the lower atmosphere and the ionosphere, as well as during the thunderstorms or the stratosphere warming events. So they can work on to analyze the data sets. And also most of the remote sensing data, we have a synthetic aperture radar images are corrupted by the ionospheric scintillations or the ionospheric corrections, as well as the tropospheric corrections are very much needed. So those synthetic aperture radar data, remote sensing data, they adapt for the atmospheric corrections. So these atmospheric corrections we can able to model. The people can work on it, and also this GNSS can be used for the sea level estimation. Normally, the sea level estimation we do with the we can do with the tide gauges by using a GNSS reflectometry. We can implement for sea level estimation, and also the soil moisture estimation also can be done as a GNSS reflectometry. For especially for the agriculture, how the soil moisture content we can monitor with the help of the GPS as a reflectometry concept. And so these are the GNSS reflectometry is another area is emerging a lot. And one more area is how the GNSS receiver is integrating with the other sensors. with, for example, initial navigation system or the 5G or a Wi-Fi or a Bluetooth. So because if you are having a drones or the autonomous vehicle applications, they need a seamless navigation, means they should not depend on one sensor. So then they need to depend on the multiple number of the sensors of navigation sensors. Let us say INS or GPS or ultra wideband module or a 5G module or other kind of a navigation sensors, parameter. So how this sensor fusion, especially for the transportation sector, with the help of AI and integration with the these LiDAR technologies, with the integration with the GNSS. These are the some of the researchers are actively working on it to integrate the GNSS with the other navigation sensors. Apart from that one, what are the navigation solutions for the GNSS denied environment? So in that way also, they can work on it. GNSS denied environment. So how the navigation solution can be adapted. And recently, the quantum communication already where the satellite quantum communication also, we can analyze these the corrections because of the atmosphere, not from the ionosphere, because most of these quantum signals works on the higher wavelengths. So ionospheric medium is not a problem. Only the atmospheric corrections are very important. So then we should understand when we are going to have a satellite-based quantum key distribution, how the atmospheric corrections can be made. So that is the another area is very, very important because most of the satellites are being launched with the quantum signals rather than the RF signals. So that is the another area, and also this GNSS can be integrated to various IoT solutions to provide the location-based services.
Thank you, sir. Thank you very much for giving lot of inputs about the research areas. Definitely, it will be useful for the research scholars. Thank you very much. Any other participants were having any queries, please ask. Okay, I think, okay, sir. So now I request Almoli Madam to the vote of thanks.
A very good evening to one and all. On behalf of the organizing committee, it is my privilege and honor to propose a vote of thanks for today's enriching session. First and foremost, I extend our heartfelt gratitude to our esteemed resource person, Dr. D. Venkata Ratnam, for delivering such an insightful, engaging, and thought-provoking session. Your expertise, clarity of presentation, and willingness to share valuable knowledge have truly added great value to this faculty development program. The concepts, examples, and discussions you provided will undoubtedly inspire and guide us in our academic and research pursuits. We are deeply thankful for the time you have taken from your busy schedule to be with us today. Your contribution has made the session highly meaningful and impactful for all participants. I would also like to thank our respected Secretary Sir, Principal Sir, Dean R&D, and Head of the Department, Organizing Committee members, and AICTE. A special thanks to all the faculty participants for their active involvement and enthusiasm. Once again, thank you, sir, for sharing your expertise with us. We look forward to more such wonderful interactions in the future. Thank you all and have a great day.
Thank you very much. I'm very much thankful for the organizers, and I am very much thankful to the participants for patience listening. So if you have any questions, also you can mail me. I'm happy to help. And lastly, but not least, I am very much thankful to the Dr. Mukesh sir. Thank you.
Thank you, sir. Very kind of you, sir. Thank you. Good evening, all. Now we are entering into the session 6. Already the resource person sir has joined. Now I request Dr. S. Rajeshwari Madam to introduce the chief guest.
Good evening. I'm very happy to introduce today's chief guest, Dr. Anindya Bose. Dr. Anindya Bose is a senior scientific officer in the Department of Physics, the University of Burdwan, West Bengal, with R&D and teaching responsibilities for 3 MTech and MSc courses. He is an alumnus of CSIR, NPL, New Delhi, and International Space University, Strasbourg, France. He is a recipient of URSI, Young Scientist Award, Senior Member, URSI Fellow, Institute of Electronics and Telecommunication Engineers. His research interest includes GNSS, navigation with Indian constellation, and online education. He has successfully implemented 16 sponsored R&D and manpower training projects on GNSS, navigation with Indian constellation, sponsored by Government of India agencies worth Indian rupees 2.75 crores. He leads the state-of-the-art GNSS laboratory Burdwan at the University of Burdwan. He is a member of the panel for standardizing navigation with Indian constellation receivers of the Bureau of Indian Standards. He is a member of Working Group 4.1,4 of the International Association of Geodesy on use of compact GNSS modules and a member of Board of Studies, CSSTEAP, Dehradun, and advisor to the Geo Interlab, IIT Tirupati, Navishkar Innovation Hub Foundation. He has more than 190 journals and conference proceeding publications and holds 2 software copyrights. He is a consultant to multiple Indian GNSS industries. He is the founder and director of Deep Technology startup company Navitro Consultancy and Services OPC Private Limited, working on GNSS navigation with Indian constellation domain. The company is being incubated under the University of Burdwan, West Bengal. Sir, we are really very happy to have in this FDP. Welcome you, sir.
Yeah, thank you very much, madam, for introducing me. And good evening to one and all. I take this opportunity to thank all the participants present here together with the college who are organizing this particular FDP on a very important topic. So my sincere thanks and gratitude is because for a long time I'm associated with the technology, trying to contribute, learning, relearning. Whatever in GNSS and Navic, it's very important, and thank you very much to all the members of your community who has arranged this, taken the responsibility of this FDP. Okay, thank you very much. So let me directly go to my presentation. I'm making the video off because to save some bandwidth, no problem. So now let me share the screen. Please let me know if you can see my screen. Just tell me yes.
Yes, sir, it's visible.
Okay, thank you very much. Okay. So my topic today is GNSS errors and correction techniques. So now it is 7:30 to 9 o'clock. We will go through this one. But please, I know it's a very tiring process because my good old friend Venkat just presented a very complex topic of which he's one of the best experts in the country. But if you sometimes feel okay, let us take 2-3 minutes or 5 minutes break. Please let me know, and let us enjoy the whole thing. That's my aim. So as already I have been introduced that I am from the Department of Physics, University of Burdwan. So I am asked this question many times in many forums, where is Burdwan? So Burdwan is a very small university town, 100 kilometers west of Kolkata in West Bengal. So many of you must have heard about name Asansol. So it's just midway between Kolkata and Asansol. So it's a university town, very rich in agriculture and obviously very good food products. And I also belong to the Navitro Consultancy and Services OPC Private Limited, which has been established under the NISP, National Innovation and Startup Policy 2019 in our university. I'm one of the three such companies who are contributing this way. So basically our company works on fully on GNSS and allied topics. So once again, good evening to one and all, and let us go here. So the agenda is like that. First, I will try to give you the current multi-GNSS scenario and advantage India, which is very important. Then, as because we need to know GNSS errors. So first of all, we need to know what are the measurements we make, and then we can very easily come to the topic of what are the errors. And obviously, when there are errors, we are there, the technology is there to remove the errors. So next is GNSS positioning techniques, comparison and theories. Then GNSS SWAP-C modules, that means size, weight, power, and cost-efficient modules, which is pretty important. Whenever we will be talking about GNSS, I will tell just why. Which is an excellent tool for education, research, and applications. And finally, the issues and future trends. If you have any question, there are two ways. You can, because I cannot see anybody now in my presentation screen, you please type your question in the comment box. I will take up one by one at the end. And secondly, when we stop, you may ask the question, or you can directly direct your questions to me through the coordinators. So these three process you please follow. No need to make too many notes. Maybe you you can take the basic points, because I will share my presentation with the coordinator, so that you don't have to write the names of the websites, etc., etc. Okay, so this is the agenda, and the disclaimer is whatsoever I will be talking today here, it is completely my point of view. Neither the University of Burdwan nor the college who is arranging this FDP, they are responsible for it. Every responsibility goes for me. I am responsible for whatsoever I am telling. Okay, now, so very importantly, whenever I will talk about GNSS, it's a question why GNSS is a so important term today. So to answer, there are many answers. So the first answer is like this. So if you look into this particular figure or graph, you can see the cumulative revenue by segment over the last maybe 2023 to 2033. Over the 10 years, you can see the GNSS and Earth observation. The expected business value is 4.6 trillion euros. So 6.3 trillion euro multiplied by 100. So you can very well understand that, okay, how big the whole market is. And it has been published by USPA, Europe, what earlier known as European Space Agency. I have taken this picture from here. And GNSS is, I would say, omnipresent in different types of application. This is one answer. And second is, maybe some 10 years ago, we could not think of, okay, I'm hungry, I am ordering food over a food delivery app, and I'm time to time, I'm checking how much time the delivery person is taking to deliver the food to me. So you can very well understand how geolocation information has been integrated with different kinds of solution and value adding it, and we are being more and more dependent on this one. I want to go to a new place. My friend or maybe relative, he or she has shared the location of his or her home. Obviously, after getting down from the bus or car or train, I simply navigate using Google Maps, and I know where I need to go. So I don't have to ask. Some 10 years ago, I used to ask other people, do you know where this one is? Most of the people, no, I don't know. Somebody will tell, okay, I know. And chances there, they will give you a wrong information. Without prejudice, I am telling. But with the advent of GNSS, the scenario has very fast change, and it will keep on changing. So if you look here, so these are the areas where GNSS is being used. Right. So that is the pretty importance of GNSS market, together with the threats and the different issues on which I will try to throw some light at the end of my lecture. But so these icons talks about everything where GNSS nowadays are being used. Nearly in every aspect of life, we are integrating the location and precise time so that it can give us our location and time and value adding to the existing solution. So If you look into the multi-GNSS scenario, I think already it has been taken care of. Somebody has talked about this. So currently we are living in an environment where there are 4 completely operating global systems: GPS from US, GLONASS from Russia, Galileo from the European Union, and Compass or Beidou or BDS from China. They're operational. Together with that, there are 2 regional systems, one from QZ or QZNSS, quasi-zenith navigation satellite system from Japan, and our own system, Ionospheric or Navic. So these are so many systems. In other words, I can tell. So in your locality, you can find there are 3-4 shops of maybe let us take sweet shops are there. But out of the 4 or 5, 2 are very really popular. The other 3 are not so popular. Why? Because they cater you good quality products, what you like. So many people, so many systems, they are being developed. Putting a satellite into the sky, and not only a single satellite, a constellation of satellites into the sky, it's a pretty costly business. So my question or your question should be, why so many countries are putting their own systems in the sky at the cost of huge cost? The answer is as because a large business potential is there, what I already have shown, and it has got both from the strategic point of view, from the defense point of view, and also from the commercial market. They are pretty important. So every country wants that. Let us have our own system, and that's why Navic has developed. From the our experience, not so good experience from the Kargil war, where GPS was denied for our defense people. So after coming back, they reported it to the government, and government decided, okay, let us have our own system. So our defense people are always safe. They can have their land navigation. So the question is, so many systems together. If you go back to the basic understanding of the GPS, so for finding out 4 unknowns, X, Y, Z, and T, we need 4 equations. Okay, 4 unknowns, 4 equations, so 4 satellites. If I can get signals from 4 satellites, we can find out our X, Y, Z, and T. So it's a pretty old idea. Why? So if you look now from India, so this is a simulation some 10 years ago, multi-GNSS Asia, it's a organ of Japan Space Exploration Agency or JAXA. But it's an organization. So they predicted that over this region, in the red shaded region, large number of satellites would be available. GNSS satellites would be available, or signals would be available. And this is the real case. So I have taken this from my place, completely at the eastern part of the country. We are getting more than 50 satellites at one point of time, but the basic requirement was 4. On the other hand, I have taken, just after a few months, I have taken the data from SBNIT Surat. We got nearly the same situation. So nearly 50 satellites we can overhead. So we can use 50 satellites. So instead of 4, we are getting 50 satellites. So if I go back here, so now, as of now, there are more than 130 plus satellites in the sky for navigation. And from India, at any point of time, if we can tell, around 50 satellites are ready for use. It looks fantastic. Okay, so we have got 50 satellites. Very good. But the question is how good we can use this technology for the benefit of human being, for the benefit of our countrymen, by using whose money through the taxes they pay. We are being educated, we are working, everything at their own cost. So it's time to give them back the best of the technology for the benefit. Okay, right. So this is what I see, that it's a fantastic technology, but it should be used for the benefit of the people of our country and our society. So as a whole, we can say that Asia-Oceania region, especially India, this region is a hotspot of multi-GNSS signal. So this is a screenshot of my mobile phone from where I have taken how many satellites are available. Just a screenshot. On the both sides, there are trees and buildings, etc. But still, I can see nearly 30 satellites. Okay, so India is a very important area or a hotspot where signals from all the constellations are available. Now let me, as because it's a FDP or Navic, I must just touch upon Navic, because I think many other experts they have discussed about the thing. So if to summarize, So this is our location. You can see we call it GNSS Laboratory Burdwan, GLB, at the very eastern part of the country. So this is 1,500 kilometers from the landmass of India. So this is we call the central service region, or sometimes it's called the primary service region. And beyond that, we have got the extended service region, which covers from western of Australia to eastern part of Africa. So just look into this. So this is the Southeast Asian countries, smaller countries, but those are using lots of GNSS based application. So Navic has something to play here. Navic can be a game changer for these countries. And obviously, so these are the originally planned 7 satellite constellation. So 3 of them are stationary Earth orbit. They are placed in geostationary Earth orbit, and 4 are placed in geosynchronous Earth orbit, inclined geosynchronous Earth orbit. So 7 satellite constellation. But in future, the plan, what I know, as far as my information, what I have gathered, that maybe over the next couple of years, it will be 11 satellite constellation with much more coverage area, right? So what are the basic advantages or differentiators of Navic in comparison to other GNSS? So in case of other GNSS, the GPS, etc., GPS, GLONASS, Galileo, their orbital height is 20,000 kilometers approximately, or they are placed in medium Earth orbit or MEO orbits. But in our case, we have placed our satellite in nearly 40,000 kilometers or 36,000 kilometers as you measure the distance above the surface of the Earth, 36,000 kilometers. So they are looking towards the Earth from a very high or larger height. So their coverage area is large and their elevation angle is much higher. So that gives us certain advantages when we will be operating within a visibility constraint situation. For example, we are in a city, canyon. On both the sides, we have got high-rise buildings. What was in case of Japan, and that's why they have developed the QGSS. Or we are passing through a very deep forest. A road is there with trees or forest on both the sides. So you can very well understand the lower part of the sky is completely blocked by man-made or natural objects. So we cannot get GNSS signals from those regions. So we can only have signals from the upper sky. Our result has shown that sometimes in the day, we do not have much choice because there is no satellite above 60-degree elevation angle. So we have got only a part of the sky from where we are getting the signals, right? But if we use Navic together with this one, Navic or QGSS, always we will have a satellite which is above 60-degree or 70-degree in most of the cases. Down south as you go in our country, higher would be the elevation angle. So there would be always 1 or 2 satellite present, and there will be seamless navigation. We will get position and timing solution without any interruption and also of good quality. So signals from high elevation angle over the service region. Second is we have got S-band signal which is not present in other constellation. So higher horizontal accuracy we have seen through our research. And secondly, off-the-shelf jammers which are maybe below say $100 that was possible to buy even from Amazon India. So they are not available in S-band. So there is less chance of jamming. So jamming and spoofing I will talk about afterwards, which is a very important topic. And then is the alert message service. So Navic together with the positioning service, it provides us alert message service on natural disasters, on cyclone, tsunami, high tide, and in normal cases, potential fishing zones. So alert message services for disaster alert and potential fishing zone for the seagoing seagoing fishermen. India has got a very large coastline, so a lot of people starting from very small boat to very large boats are there. But Navic provides a service through which they provides the alert message service. And thirdly, the advantage in ionospheric research. So come here. So we can see we have noticed. So already my friend Venkat, he has told that how atmosphere affects the GNSS signal, and I will also talk more. So you can see during the same event, we can see the effect of the atmosphere is much more prominent if you look to the red curve here, where we are measuring the S4 index. So this is for L5 band and this is for S band. You can very well understand or very well see the S4 index is much lower in case of S band signal in comparison to L5 signal. This is number one. And number two, so they're less prone to, or there is some resistance to degradation of the signals due to the ionospheric events. And also we have seen, it is also our research, we have seen that as because the ionospheric Pierce point of the GNSS satellite, NAVIC satellite signals remains nearly fixed, or it varies only for a small amount. So we can make for any region or from any location, we can we can probe certain areas of the sky continuously. So this is a research where we have taken the same data from two parts of the country, one from our place near Calcutta, and the other part is near Kolhapur. It's called Panhala. So together we did the experiment, we collected the data and processed them together. But you can see there is certain, what is the difference? It's not the main point of interest here, but you can see from the same satellite, same time, we are getting two different signatures of the atmosphere. So these are the advantages of the NAVIC, which is beneficial for education, for real life application, and also for research. Okay, now let us go to, because we will be talking about GNSS errors. So before going to GNSS error, we need to understand what are the GNSS basic measurements. I have got a GNSS receiver, maybe a geodetic receiver or a small receiver, or maybe your mobile phone. I will talk about that if time permits. So what they actually measures? Does they measure your location now? I have to create already, you know, the basic equation Ri equal to whole root xi minus x whole square plus yi minus y whole square plus zi minus z whole square whole root plus minus c delta t. Okay, so here xi, yi, zi is the location of the ith satellite, and xyz is my own location. By together simultaneously or concurrently solving four such equations, we can find out x, y, z, and t. Right? But how this is done? So on the left hand side there is measurement. On the right hand side, you know, there are values what we are getting from the satellite signal. So basically, a receiver channel, that means a particular electronic path in your receiver, they measure the basic these types of things. First, the pseudo range, okay, or the pseudo range, that means the range, that means the distance between the satellite and your satellite antenna and your receiver antenna. So this is the range, and as because it is not fully correct, we need to make some corrections. That's why we call it pseudo range. Okay, using codes, you know, code-based measurements, carrier-based measurements, I will touch upon that one. Then it can measure the Doppler. As because the satellites are moving fast, if we take the MEO satellites, their speed is approximately 11 km per hour with respect to a static receiver. So obviously there would be change in the transmitted frequency, let it be L1, L2, L5 or S. So it can measure the Doppler. Then it can measure the phase of the carrier. So the navigation data, it is, I would say, it is superimposed on the carrier signal. And nowadays our receivers can measure what is the phase of the carrier using phase lock loops at the receiver. And fourthly, the carrier to noise density, or you can say what is the signal strength. So these are the basic four measurements what a receiver or a receiver channel can make. A receiver has multiple channels, maybe 184, 216, or even nowadays we can see a 812 channels, etc., etc. So each of the channel can measure this, and this channel, the measurements are used together in the processing engine to give you or to give me the PNT data, position, navigation, and timing data. Okay, so most receivers generate single points navigation outputs, that is position, velocity, heading, etc. Measurements of all channels concurrently. The time at which a set of measurements is collected is called a data epoch. Okay, or we call it GNSS time, let us call it GPS time. At every instant when we are measuring it, we call it an epoch. And nowadays, the receivers, they're capable of, earlier, I can recall long ago, some 30 years ago when I started working, my receiver could only take data once per second. That means the data rate was only 1 hertz. I repeat, only 1 hertz. Every second, it is giving me my position output. And that too in a completely ASCII output, what we know as today know as an NMEA data output, where directly I'm getting the latitude, longitude, altitude, number of satellites, what is the signal strength, etc. It can give out. But nowadays, even the very low cost receivers, very low cost, whenever we talk about that, that means below $100, they can give you 20 hertz data. That means every second they are giving out a set of 20 measurements. And slightly higher cost receivers, they can give you, maybe the cost is around 70 to 80,000 rupees, uh, like that, only the receiver hardware, that can give you 50 or 100 hertz data. So you may ask, why uh, 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 such high data speed is required, that every second we are getting 100 sets of data output? Is it really required? It's a question what I put before you. As because today is the probably is the third day, you have heard a lot about GNSS, so you know a lot of applications, and you just try to find out what may be the applications where we need such high data rate. But obviously, high data rate, it comes at the cost of many things. Obviously, higher price, but most importantly, higher data rate means how to handle this huge amount of data. So at a point of time, we are, say, seeing 40 satellites. So from 40 satellites, in each of the channel, we are generating 100 data per second. So 40 into 100. So you can understand, and that data is not as easy as what we call the NMEA data. It comes in the form of raw data, or what we call the RANX data. So they're very difficult to handle, but at the same time, they are providing me extremely good flexibility to understand the data, to process the data, and to use it as per our requirement. Okay, so the basic idea is that GNSS measurement consists of pseudo-range, Doppler, carrier phase measurement, carrier to noise density. Now, let me talk about just a little bit about code-based measurement and carrier phase-based measurement. Right. So what they signify? You know that in case of GNSS, the data is multiplied with a pseudo-random noise code, which is unique for each satellite in case of GPS. In case of GLONASS, they use FDMA. The codes are same, but the frequencies are different. But for the making our life simple, let us follow the case of GPS. In case of GPS, each of the satellite has their own assigned PRN code, pseudo-random noise code. The basic GNSS data of 50 bits per second, they are multiplied with this one, and after that, they are superimposed on the carrier signal, maybe in the L1 frequency or L2 frequency or L5 frequency, and in our case, nowadays L6 is also there in QZSS, and in our case S-band. So the spectrum is full. Okay, so how we find out the range? So if you recall the old the basic equation, Ri or Ri equal to already what I told. So on the left hand side we have got a measurement, what, or an estimation. So our receiver estimates the distance between the satellite and the antenna phase center. How it is done? It is basically done in two ways. So here I have taken this figure from Pratap Mishra's book. So here you can see, so this is the code. Okay, so what we do, say satellite PRN number 2, it is transmitting a signal. I know the PRN code structure. So in the receiver end, we try to match a locally generated copy of the PRN code with the received copy of the PRN code. And we do a time shift. So when the cross correlation is very high, that means that is the time of travel of the signal from the satellite to our end. If we multiply it by C, that is the distance, or that is the range. It is more or less simple, but you know, we are trying to measure this distance using a scale whose say primary units are large, so errors are higher. So code-based measurements, they're very simple, but they are prone to errors. Up maybe some 10 even of some 10 years ago, all code-based measurements were the only possible solution, and we were happy with the code-based measurement 10 to 12 years ago. Okay, but we know in case of GNSS, we need much higher. We are not satisfied with the precision or accuracy level what the code-based measurements provide us. We want better. We always want better. They provide us around 3 to 4 meter or 2 to 5 meter solution accuracy, but we are nowadays we are talking about sub-meter, centimeter, even millimeter level accuracy. Believe me, we can nowadays sitting in 2024 or 2025 or at the end of 2025 or early 2026, we can cater the need using very low cost solution. So what they did, they tried to measure how many number of cycles has passed from the transmission of the signal from the antenna when it reaches our antenna. So suppose we have got it say for example from the GNSS antenna, 20,223 complete cycles of the carrier frequency, what you can see, that has elapsed and reached my receiver. And obviously it would not be a complete integer. Some small part would be there which is a part of a total cycle. So we have to measure n number of complete cycles divided by n by x part of the cycle. So if we can measure it, so now we are measuring the distance using a much smaller scale. So obviously we can measure it, our measurement will be much more accurate. And what we will do, n into lambda, that is the wavelength of the carrier signal. So this is the distance plus n by x into lambda. So we can measure this distance or range between the satellite antenna and my antenna up to a very precise extent. But the problem is, suppose it occurs every day in our daily life. We are measuring maybe I have purchased a tokri of mangoes. Okay, I'm very fond of mangoes. That's why it came to my mind. So I have a box of mangoes. I am counting how many are there. In the meantime, somebody called me. I told him, okay, just wait. Let me finish the counting the mangoes, and I'll talk to you. So now, after coming back, I think how many I have counted? Was it 19 or 18 or 20? This very readily occurs in our daily life. This also occurs here. When we are trying to measure how many numbers of complete cycle, so we are measuring a distance of 20,000 kilometers with a scale whose unit is 20 centimeter, around 19 point something, let us take it 20 centimeter. So you can very well understand, missing one cycle or adding up extra one cycle, it is quite possible. And we call it ambiguity, cycle ambiguity. So in this case, for carrier phase based measurement, ambiguity resolution is a challenge. There are many methods, mathematical methods. One of the method, the name is lambda itself, developed by Peter Tunisian and his group, that how to take care of this ambiguity resolution. So if we can resolve the ambiguity, then this is the best method. You can very well understand. So if we compare code-based measurement, they are very easy, but their error level or their quality is not that good. Just one moment. শুকাবো আমি ইয়েতে রয়েছি, সেমিনারে রয়েছি, আমি 9টার পর কথা বলবো। Okay, not that good. But in case of carrier phase based measurement, it's a extremely complex mathematical process. If we can achieve that mathematical process, we have got very good. So whenever there is a complex mathematical process, you know, the computational load on your GNSS chipset, that is quite high. So if we can handle that, then there is nothing like carrier phase based measurement. So so using this one, we find the pseudo range. Don't bother about what are the terms there. Just this is a pseudo range measurement and this is a carrier phase based measurement. So some extra terms are there, right? So here we have taken care of the ionosphere, the troposphere, etc. We have taken care of. But these are the two fundamental types of measurements. So what I have tried to give a better, I would rather say a better visual of the how the code and carrier phase based measurement they work. So I have given this. So I'm simply, as because I have told this, I'm skipping this one. So the question comes, so code based measurement, similarly the carrier phase based measurement. Okay, now the question comes, what is the strategy of modern day receivers, how they perform, whether they do fully carrier phase based measurement. Definitely I will expect that nowadays, as because all the problems has been solved, the algorithms are in the market, we will go for carrier phase based measurement. But the manufacturers is very I would say brilliantly they have taken care of the problem. So what they do, as because code based measurement is very easy and it does not require much of my computational load, so first of all they make a carrier phase based measurement. Then using this one, they try to resolve the problem what is coming out of the carrier phase based measurement. So it's a always a code plus carrier phase based measurement, and as an user we get the best possible results within the best possible time, and most importantly at the best possible cost. That is pretty important. Whenever we will do something, as an engineer I have to think about the together with the computational load, we have to think about the financial load of what my solution is bearing, whether my solution can be popular in the market. That will give my answer, until and unless I can rationalize the cost. So using these two techniques together, nowadays I'll talk about that nearly at the end of my lecture, that many receivers are now available within very good price. We can provide the users very good solution. Now, one point, because we are talking about errors and techniques. One point I think it needs to be raised, because in most of the GNSS related papers, you will find two terms. One is called the precision, and second is called the accuracy. And I have seen many times they have been used interchangeably. Sometimes at the starting of the discussion, they have used accuracy. At the end, they are using precision. But there is a basic difference between them. Take the case of a archery event, archery competition. So this is the bullseye. So my picture tells everything, that this is highly accurate and highly precise. This is the accuracy is low. It is away from the center point, but the precision is excellent. All the arrow shots, they are concentrated on one point. This is the accuracy is high, but the precision is low. And finally, these are neither accurate nor precision, nor precise. So how we will define precision and accuracy? It is I have taken this simply from internet. So in precision means what is the level of scatter of the estimations what we are making for the GNSS. In case of GNSS, we are discussing what is the scatter of the estimation what we are in 2D, for example, here for the solutions where we are getting. What is the 2D RMS value? Or in case of the 3D RMS, what is the spherical error probable? Right. So if they are closely spaced, I will say they are precise. But if the measurement is made with respect to a particular point, that means a reference point, then this measurement would be called an accuracy. So I repeat, so we are making a measurement and estimation. We are making the estimation and getting this type of estimation. So the scatter is very low. I will tell them they're precise. Whether or not they're accurate, I have to take, because doing this measurement 2D RMS, I need a reference value. If we make the measurement with respect to a reference value, for example, here, then I will call it the accuracy. If not, we will call it a precision. So our expectation always would be like this. It should be highly accurate and highly precise. But believe me, in most of the cases, we will find we can get very high precision and not very accurate. And the opposite. So what type of solution we want, that depends upon what type of application we are talking about, right? But we have to bear in mind, although interchangeably used in many cases, accuracy and precision are two different parameters. If the precision measurement is done with respect to a reference point, then it is accuracy. If the precision measurement is done with respect to an average point of the solutions, then it is simply precision. Right. Now, when I talk about this to my students, they always ask, sir, you are solving equations, 4 mathematical equations together. So their solution should be unique. Why should there be any variation? But to start the discussion, let us see an example. So here, this is the reference coordinate. Where it is. So this is the reference coordinate, right? The star. So we have on our laboratory on the rooftop, we have got a reference antenna. Using the reference antenna, using PPP, I will talk about precise point positioning. We have found out the reference coordinate. Then for a normal day, there is no disturbance. For a normal day, we took the whole data and make some average, non-weighted average, simple average. We found that it is lying here. So here you can say this is around 2.2 meter, or say 222 centimeter. So you can see some 10, 15, around 10 centimeters or less than that. Okay. And the scatter for a normal day, we can found their scatter is surrounded either the reference location or surrounding the average location, right? But we took the data on a day when there was a severe cyclone in our part, what is known as Amphan. Okay, in middle of 2021, I think, in May. So during that day, normal day, and this is the Amphan day in May, and this is in June. So you can see in normal day, even in a normal day, there are scatters. And in the Amphan, the scatter was much higher. We reported this. Okay, so this is an obvious question. We are solving for mathematical equations. Their solution should be unique. But in the result we are finding, when we are plotting them, we can see a huge scatter. Obvious question is why? The answer is very simple. There are errors in the measurement, because in the main equation on the left hand side we have got measurement. So if we can measure it accurately, our solution would be accurate. And if we can measure it inaccurately, our solution would be inaccurate. And if our measurement varies instant to instant, obviously the solution X, Y, Z, and T will vary. So the Ri term, what we are measuring, that keeps on changing. So anybody will ask why they will keep on changing. So that is the answer I want to present before you. When we are using a GNSS based system, so these are the GNSS satellites, or say GPS satellites around 20,200 kilometers. You may ask me why you have not taken it from Navic. Yes, in case of Navic it is also true, but as because it is easily available from this book, I have taken the picture and put it, because the basic essence remains the same. We have got 3 classes of errors in case of GPS or GNSS. First is the satellite ephemeris error. That means, if you go back to the basic equation, Ri equal to xi minus x0 whole square, that xi means the satellite is transmitting its own location every instant. So if the location measurement, what it is that particular satellite is estimating, that is in error, obviously that will creep into our equation. So that is called the satellite ephemeris error. Second is the satellite clock error. Satellite clock error, all the satellites everywhere, it's a game of 1023, right? 1023. Why 1023? 0 to 1023, 2 to the power 10. So as because it's a digital system, it's a game of 1023. Okay, the satellite clock generates 10.23 megahertz, not 10 megahertz. Okay, so these clocks, they are synchronized with a ground clock, and they may have error any estimation. So it has got some errors. So however small it may be, and if you convert 1 nanosecond, 10 to the power minus nanosecond is to distance, so you can find that is an appreciable value when we are talking about centimeter or millimeter level accuracy. Third is relativistic effects, as because the satellites that those who are created, or those who are developed on the surface of the earth, and where they are moving, the gravitational pull is it has got 2 different values. So general theory of relativity comes in, and the satellites are moving with very high velocity, so their special theory of relativity comes in. So one of them try to make the clock faster, the other tries to make the clock a bit slower, but we have taken care of this thing. So we make the clock offset on the ground. When it reaches to the orbit, it properly operates on 10.23 megahertz. Then satellite geometry. Satellite geometry means how the satellites are scattered over the sky. It's called satellite geometry. It is also pretty important, but in a multi-constellation environment, it has some of its relevance. Then comes the ionospheric delay, ionospheric scintillation. So as because EM signals are passing through the ionosphere, I think when my friend Venkat has talked, so I'm not that person who can add on something. Yeah, just one moment. হ্যাঁ দাদা আমার একটা ক্লাস চলছে আমি ক্লাসের পর 9টায় ফোন করছি ওকে ওকে So, as because they're passing through the layer of charged particles, what is called the ionosphere, and which varies in depth, in density, in velocity, everything which changes. So, while passing through them, because of the charged particle layer, we have got ionospheric delays. So, while we are thinking that it should be a straight line, well, when I'm thinking that this should be a straight line, instead of a straight line, it will be a slightly bent uh, uh, ray when it's passing through the ionosphere, which is called the ionospheric delay. Second is as because the change of the concentration of the electrons in the layer, ionospheric scintillation occurs. You must have noted that only last week Airbus has noted that many of the aeroplanes, they are having severe disturbance due to ionospheric events or the solar flares. The solar flares are affecting the ionosphere, and they are in turn affecting the navigation system and also other systems of the aeroplane. It's a very important concern for all of us, because nowadays we are pretty much dependent not only for navigation but also for air travel, but also for satellite based communication, for remote sensing, and all the signals are being affected. And intersystem biases. So when we have got more than one system, obviously we will try to use more than one systems together to have redundancy, better satellite geometry, improved solution, etc. But all of the systems, they have been developed by different countries. They have got intersystem biases that is also taken care of by the I would say by the algorithms. At the receiver end, we have got a few types of errors. One is multipath, which are not intentional, multipath errors, and receiver noises. As because receiver is an electronic system, so electronic systems have their own noises, but we can estimate up to certain extent that these are the possible noises, and accordingly we can take care of that one. And multipath is the reflected signal. So if I go to the next slide, so this is the direct signal, and this is a reflected signal from this one. So my receiver, it is very much possible that my receiver cannot distinguish whether it is getting the direct signal or whether it is getting a reflected signal. If it thinks, within double quote, if it thinks that this is the real signal, the multipath signal, so instead of R, it is getting R plus delta R. So already in my measurement some error creeps in, right? Secondly, there are unscrupulous people everywhere who are trying to make us fool. So jamming signals are there. Intentional, there are certain unintentional jamming from electrical lines, from other electronic sources, but there are intentional jamming too. My enemy doesn't want to leave my system in a very good condition, so they are transmitting jamming signals. That is one type of problem. And second problem, I think many of you at least heard the term what is called the spoofing. SPOOFING, spoofing. That means to make my receiver full, I am sitting in Burdwan, and my receiver, when calculating my position, it will show that I am sitting in Kolkata. So that is now possible, and so it is a serious threat. Okay, so these are the error sources. Now I know that GPS solutions, they have got scatters, but we need better solution. So when we investigated, we found these are the errors. So if we can mitigate the errors, so the scatter would be low and we'd get good quality solution. As simple as that. So resolving these errors is the key to enhance performance of a GNSS receivers and to enhance the quality of the solution. The more errors a receiver can eliminate, the higher the degree of positioning accuracy and reliability it can achieve. Receivers hardware and software design and implementation impacts the effectiveness of error resolution. So now we understand that there are many types of errors, and let us together take care of these errors. So I have written this. So I have discussed at least clock errors, orbital errors. So these are the layers of the ionosphere, ionospheric delay. So how it affects? Similarly, tropospheric delay. Below ionosphere, there is another layer, what is full of basically water vapor. So they also causes a delay, not as prominent as it is the case in case of ionosphere, but they affects, right? Other errors, already I talked about receiver noise, multipath. So the best way to avoid multipath is to keep your receiver in a location. So in a location where there is no reflector. Even if there is no reflector, you can very well understand that from the ground there will be reflections. Although when it is being reflected, certain thing changes. The phase of the signal change, or polarization of the receiver changes, or the signal changes. That is good thing for us, but they can affect. So a very easy thing is just to put a maybe a iron plate just below the antenna, so that all the signals reflected from the ground, they get absorbed there, or they generate a signal there which does not reach the, or you can you are actually shorting them, so they are not reaching the antenna phase center. So you can see, so these are the different kinds of installation of GNSS receivers. So this is our reference receiver. You can tell, okay, we can see trees there. Okay, number one, the trees are much below the antenna level, and secondly, time to time we make trims of the trees. The time when the photograph was taken, at that time they were that high. So we need to put our antenna as much as possible in open sky condition, but as far as practicable. So definitely you may tell me, how come? I'm moving in a car, or my car is being tracked. I'm using a tracker. I always, for your sake, I cannot always move through the highways where both the sides are open. I have to enter into the city. There my office is there, or college is there, or my business is there, or the shop is there. So how come? That's why you have written as far as practicable. Okay, and but for a continuously operating reference station, the last slide what Venkat was showing, I saw he was talking about CORS, continuously operating reference station. We need to understand whether there is any multipath effect or not, multipath effect or unintentional jamming effect. First, after setting, we need to analyze the data, do it, repeat it for a few days, analyze the data, see their presentation, or see their outputs, and then we can be sure, okay, there is no multipath or there is no unintentional jamming. For normal operation, we cannot do that, but for any research laboratory who wants to start a course operation, it is mandatory that you have to understand the fully, because whenever we write paper, many times it is asked, you are telling that you are operating in a multipath free environment. How can you prove that it is a multipath free environment? Then we show the graphs or curves through which we have analyzed the data. And we keep on doing every 6 months, 7 months like that. So to satisfy ourselves and also to our reviewers and our peers. Now, I talked about the satellite geometry. Satellite geometry is another very important term. Satellite geometry means we have got on the upper hemisphere, we have got satellites whose signal we use for navigation. So if all of them are clustered together in one side, we call it a bad geometry, represented here. This is a good geometry, they are scattered over the sky, and this is although good, but they are obstructed. So this is our research that we saw that if we can use 20 or 21 satellites, not more than that, because more than that satellites will enhance our computational load. So we are getting a very good DOP value. It is expressed in terms of DOP, dilution of precision. We get a very good DOP value around 1. So this is so satellite geometry is pretty important, but as because nowadays we are in a multi-GNSS environment, we have got lots of satellites. This particular topic, it is not that important nowadays. And obviously, I talked about this malicious and unintentional interference with GNSS and intentional jamming and spoofing. Now, so let us skip this one. So there are effects of radio frequency interference on GNSS output, loss of. So what happens? Even if the radio frequency interference is too high, the receiver may completely stop working. It can decrease the measured signal strength, increase in noise on the pseudo measurement, increase in noise on the phase measurement, increase of cycle slips. Cycle slip means what I already told. How many numbers? n-1 or n-2 or n+1 or n+2. That many, so this type of problem occurs because of the radio frequency interference. So unintentional japping, there are various examples. One of the classic case was GPS light squared interference. So light squared was a satellite-based internet company in US. So their signals were interfering with GPS signals, and probably that was those were settled out of the court because light squared proceeded with all possible legal protection. Okay, so law of expertise in the lawmakers. Remember, spectrum allocation is a regulatory issue, not a technical issue. Mostly bureaucrats do that, and in many cases, I would say non-presence of a proper technical person gives rise to this type of problem. Okay. Anyway, this is a classical example I need to raise before you. So this happened in Newark Airport, NEWARK Newark Airport. What was the problem? It was found that every day during some part of the day, all the GPS receivers in this particular airport they were not operating. That means some jamming was occurring. So investigation began, and afterwards it was found that you can see the road here, a car is passing. Through this road, it was found that a truck driver was passing every day at a particular time, around a particular time, and to keep stop tracking by the owner of the truck driver used to use a GPS jammer, off the shelf GPS jammer, which looks like this in his truck. So when he was passing through this highway, his device was completely jamming the GNSS receiver. So you can very well understand in life and property critical application, it is very, very dangerous, and we have to take care of this one. So this is the takeaway up to which we have discussed. It is prone to multiple errors. We need to take care of the errors. So what are the methods? The error removal methods, or we call the positioning techniques. Basically, we subdivide them into three classes. First is absolute point positioning, or single point positioning, or single point positioning system, or SPS, what is shown here. Second is the relative positioning. That means here you can see it is as simple as that I have got a receiver. So for example, your mobile phone, I am getting the data. My GNSS chipset is doing the measurement and giving me the result. Very simple, but the accuracy is low, order of 3 to 5 meters. Then comes relative positioning. Relative positioning, you can see here, there is an infrastructure. We need a master receiver or base station, and we need a rover receiver or a slave receiver. The master receiver receives the signal, calculates the error, finds out the error, and transmits it over wireless channels to the user. The user uses it and improves it solution. So that's why it is called relative positioning. So standalone positioning, SPS. Second is relative positioning, and the third one, the precise point positioning, or PPP. In case of precise positioning, the infrastructure is like SPS, but the data is post-processed. In case of SPS, I'm collecting the data at say 27 seconds. At the same instant, I'm getting the result. But in case of PPP, what we do, we collect the data. After collection of the data, we request for some correction data. The correction data comes to us after certain time, maybe after certain hour or a week or after 15 days, it reaches us. Then we use the data to improve our location. And so these are the three techniques. This is a very important thing, the trade-off between the different error removal methods of the GNSS signal. Forgive my dot there, it's not the full stop. Depend on the user requirements of individual actuation, level of accuracy required. Suppose I'm moving in a bike, 2-3 meters is quite good for me. I am doing some precise agriculture. I need centimeter level precision. I am doing a research on cadastral plate movement. I need millimeter level accuracy. So if for a maybe who is moving in a rather motorcycle or bike, if he or she wants millimeter level accuracy, it is not required for him. Unnecessarily, he or she has to spend a lot of money to go there. For him, SPS is quite good. On the other hand, if I give a meter level solution where the total tectonic plate movement is a few centimeters per year, obviously there will be no takers. So the compromise has to made level of accuracy required, how much system complexity I can bear, what is the solution availability, what is the reliable, I mean, how reliable is our solution, and most importantly, the cost. It drives the whole market. Which receiver for what purpose? It is driven by cost. If I get extremely good quality solution at a very low cost, nothing like that, but it doesn't happen. Now, so what are their accuracy level? So I've taken these two figures from the same book, Springer Handbook of GNSS by Peter Tunisian. So it's a very good book for those of you who are interested more in GNSS. It's a very good book. You can go through it. All the chapters are very well written by the best experts of the globe. So if you look here, it is the baseline. Baseline means what is the distance between the base and the rover. We call it baseline. In case of GNSS, there is no baseline. Or in case of SPS, SPS has been converted here as GNSS. I can walk anywhere in the globe, but it is showing that the accuracy is 10 meter. It's not the case. The accuracy would be a bit better than that. It would be, nowadays, it would be at the order of 3 to 4 meters. Courtesy multi-frequency, using 2 or 3 frequencies together, we can take care of the ionospheric delay, and that's why we get the better accuracy. Different types of models, etc., etc., we get 2 to 3 meter accuracy. So if we go into DGNSS, differential GNSS, you can see up to a distance of around 1000 kilometer, it is showing that it will give you below 1 meter accuracy, right? In case of RTK, you can see it with around 60 to 65 kilometers. It can provide us 1 to. So higher the distance, lesser would be the accuracy. At a distance of 10 kilometer or so, we can get around 1 centimeter precision. But here, what has been shown by PPP, it is not correct. It has shown 10 centimeter, but using very low cost PPP, nowadays we have got better than 5 millimeter by 5 millimeter precision. Accuracy, not precision, 5 millimeter by 5 millimeter accuracy. So if you need few meter level, go to SPS. You need centimeter level, sub meter level, go to DGPS. If you need higher, that is order of few centimeters or decimeter level, use RTK. If you need millimeter level, go for PPP. So that is the, you can say, the rule of thumb or a very ballpark prescription. Okay, so it has been shown there. So let me talk about a bit about the different positioning techniques. Let's start with SPS. Already I told. So we are taking data, we are making average, we are getting 3 to 5 meter solution. So how we can improve the quality? Number one, modeling, use of multi-frequency receivers, where the frequency difference between two used frequencies, that is used to correct the ionospheric delay. And using that one, we get better solution. So SPS, it gives us 3 to 5 meter solution. And in many cases, that is excellent for many of the applications. Next. So this is one example from our direct research. So you can see this is the east error. The east error, it is modulating even plus minus 1 meter. That means within 2 meters. And we have checked different very low cost receivers. Even using the low cost receivers, not the diamond one. The diamond one we are using a very high grade geodetic receiver. So it is concluded in this paper, we have shown that the quality of solution of the low cost or the SWAPC modules nowadays are as good as, I cannot say better or equal, nearly equal to the geodetic receivers. So they are excellent tools for research and solution development. So here you can see in the eastern to north error, they are within 2 to 3 meters, but in the up error, the up error is much higher. Now differential method. So differential method, that is the idea already what I have given. So this is the base. The base knows its own location. The better is knows its own location. So if I do PPP, I can know my own location at the millimeter level accuracy, and that is fed to the receiver. Now, at this particular instant, say 8:34:25 seconds, I am getting my location. I know my exact location. So I know what is the error. So I now transmit, or the base now transmits this error in a region around 40-50 kilometer. Why 40-50 kilometer? Because the ionospheric condition 40-50 kilometer surrounding the base is more or less same. If you go beyond that, the ionospheric condition change and the error parameters will not match. That's why the RTK is constrained with a distance. So what happens if I go beyond, say 60 or 100 kilometers, I need another base. After 100 kilometer, I need another base. So many of you must have heard that the Survey of India now putting a core station network over our country so that people can start using RTK. People now can use RTK for different purposes. Still now RTK is not that popular. So this is called differential GNSS. In case of differential GNSS, we use code-based measurement. And in case of RTK, the very same thing, only the measurements are in the carrier phase-based domain. So code-based measurement, first of all, let us find out the base station location, X, very precisely. Then find out the instantaneous error, transmit the error over different wireless channels. The rovers, they are also equipped with low cost or any GNSS receiver, which is doing SPS. So it knows SPS location. It is using the correction data. Using the correction data, it is improving its location. So here we have got data plus error. Here we have data plus error. If we can calculate the error here, so and transmit it error here, so data plus error minus error, so we will get only data. So that is the basic idea of differential GNSS. If in case of differential GNSS, code-based measurement is used, it is called DGNSS. If carrier phase-based measurement is used, we call it real-time kinematic or real-time kinematic, or we call the RTK. What is the advantage? In both the cases, the advantage is we are using or we are obtaining very precise solution or very accurate solution and instantaneous solution. That at this moment, I am getting my solution. In case of PPP, I told you that I am collecting data, then processing the data, waiting for a few days or maybe few hours, then collecting the data, and then fusing the data with my raw data, I am giving solution. In many real life application, it will not work. But in many research application, it's fine. So that's why we have got different types of application and different types of methods. So for real life application, so it is given here. So differential GPS or differential GNSS, it is talked. You have heard about the S-bus. Actually, the differential data, the correction data. So but if I transmit the correction data over radio, it has got some limitation. So the correction data is transmitted from the satellite, communication satellite, and it's called satellite-based augmentation system or S-bus. Gagan is the example of one of the S-bus. Each of the countries now, they have got their own S-bus. For example, WAS in case of WASS, wide area augmentation system. In case of US, in case of European Union, it's called IGNOS. In our case, it's Gagan, like that. So what is done? The carrier, the correction data, they are calculated, they are uploaded into the satellite, and depending on the location of the user, from the satellite, we collect the correction data and improves our location. So using S-bus, we can find out our location, as because it's a differential GNSS, but with a higher coverage area. So the solution would be at the order of meter level accurate. Similarly, in many cases, ground-based augmentation systems are also used, what are called the GBus. Now let us come into real-time kinematic. We have got 20 minutes more. Real-time kinematic RTK. The concept is very same, only here we use carrier phase-based measurement. That's why it's much more complex. But it can give one order of betterment. We can get decimeter around 10-12, around 10 centimeters is very easy. Very easy. Getting 10 centimeter accuracy using RTK is very easy. If the baseline length, that means distance between the base and rover, is order of say 10, 15, 20 kilometers. Right. Beyond 20 kilometers, it will go 12, 13, 14, like that. So I can show you just one example. Yeah. So this is an experiment what we made. So the base was developed using the base was it is actually a 24/7 base station what always works. Anybody interested can contact us for getting the Entrip service. I'll talk about the Entrip. So it is transmitting the error signal and putting it to the internet. From the internet, the data comes to the rover. The rover we have used a $90 GNSS receiver, and you can see up to a distance of 288 kilometer, we are getting below 60 centimeter accurate. And here you can see it is below 10 centimeter accurate results. So once again, this is another result what we have published. So okay, so how the data will, how the correction data, we call it RTCM, real-time correction message. So real-time correction message, it can be transmitted from the base to the rover using two methods, using radio, here you can see, or using internet. So we are uploading it into the internet. Wherever there is some internet connection, the user can download it using Entrip protocol. So it is called network transportation of RTCM using internet protocol Entrip. But bear it in your mind that the distance between these two, that the base and the rover, that is a constant. We cannot go beyond, say, 100 kilometers. You may tell me you have gone up to 288 kilometers, but it was an experiment. That's why we were happy with getting 60 centimeter. But in most of the cases, your requirement would be, say, around 10 centimeter. You will not get 10 centimeter at a distance of more than 100 kilometers. Okay, so these types of different types of, and in this case, we use a computer what is called the Entrip caster. So Entrip, network transportation of RTCM message using Entrip protocol. We have Entrip caster that casts the correction data. Anybody has the credentials of the Entrip casters, that means username, password, blah, blah, blah. So he or she can access the data and can use it. Now the question is, so this is RTCM message. Don't put too much importance now. At least now, we don't need to put too much importance here. So now, how to do RTK or how to do DGPS? So there is an excellent software. The name is RTK Lib. RTK Library, RTK Lib. It has been developed by Professor Tomaji Takashu from Tokyo University of Marine Sciences. And believe me, our group has got very good contact with TUMSAT, because every year our students are trained there and they come back and they teach us the new features of this type of measurements, right? So we learned that Professor Takashu developed it over 10 years, nearly 12 years. Over 12 years, he worked on this one so that everybody has got a RTK engine. That means a software. And instead of selling it, he has uploaded it into GitHub as a complete freeware. Anybody can download it and use it. So those of you who are really interested in processing GNSS data, doing RTK, there are many other commercial software also. But for our purpose, for the R&D purpose, I think RTK Lib is an excellent tool. But you need to learn RTK Lib. So what we planned that maybe by the middle of January or third week of January, we will be doing one workshop on processing data using RTK Lib. So we'll invite through the coordinator those of you who are interested. But obviously, all the participants need at least basic understanding of the different types of GNSS data. Okay, so those of you who are interested, download RTK Lib. It's not that, because the help file is quite good, quite vividly it has been written. But best method is to learn RTK Lib from already who are using this one. So always this is the best method. So using RTK Lib, one can do SPP. SPP is anyway possible. One can do RTK, one can do DGPS, and can see what is the difference is going there. Now the final one, the PPP. The PPP, precise point positioning. What is the concept? The concept is, I am collecting data here, and after collection of data, we are getting the correction messages. I repeat, the correction messages for ionospheric correction, for tropospheric correction, for satellite orbit correction, for satellite clock correction. All the data, they are generated using a voluntary network, what is called the IGS, International GNSS Service. It's a voluntary network. Currently, there are 500 plus stations. So in India, there are now 5 or 6 stations who always collect data and send it to IGS network. And there are people in IGS network who voluntarily process the data and finds out what are the corrections and send it to the users. So I told for PPP, I am collecting raw data, then I am waiting for the correction data, I am collecting it from IGS service, then putting it there and getting my improved solution. So it's a, those of you are interested, I will request you to do this igs.org. So you will find how a mutual global collaboration can benefit the whole humankind. So you don't have to pay, and nobody pays you for uploading your data. It's a completely voluntary but very strictly maintained consortium, so that the data quality is always the best. Also, there are online PPP services. For example, from OSPOS, from Australian government, then from USA, NOAA, NRCAM from Canada, where you can do, what we can do, you can collect the data and upload into their website, and after certain time, maybe after 6 hours to 24 hours, they will give you back your PPP position. So that is another method. Either you can use RTK to do RTK, or you can collect data and upload it here. So that's another method. So there are many post-processing software, RTK, GLab, Gamete Globe. The best possible solution is Barneys. It's very costly. Only the cost nowadays is around 10 to 12 lakhs, the basic software cost. But believe me, it is developed by an university, the University of Bern. But one has to learn it for maybe 2 to 4 years, take part into their training courses. Only then a person can fully understand the Barneys. Similarly, Gypsy, etc., Magic GNSS, it's a product, it's a commercial product. So there are many online PPP services, paid, unpaid, by government, by other agencies or commercial agencies like that. So I want to show you another example. So we are doing PPP. Okay, so position uncertainty of 95%, we are getting, so in the east we are getting 0.005 meter, that means 5 millimeter by 3 millimeter. Here, using GPS and GLONASS together, you can see it is repeating. In 2021 we did this experiment, 3 millimeter, 3 millimeter by 4 millimeter. In the x coordinate, 3 by 4. In the z coordinate, it is around say 12, 13, 18, that means order of centimeter. So, and in this case, we have used a very low cost receiver, of which I will talk next, u-blox F9T. u-blox F9P. So already I have given, so what is the horizontal accuracy, what is the coverage, already we discussed this. I have taken this from the very same book, and to have a one-page summary, I have collected it. Now what I think, we are learning GNSS for application, either for education or for research or for real life application or any kind of thing. So we should at least have some idea what are the different kinds of hardware that is available in the market. So there are many softwares, there are many kinds of hardware. So these are the geodetic receivers. You can see very well they are quite well packed, everything is there. It has got their own operating systems, they can work as encrypt server, they have got inbuilt batteries, everything is there. And you can see the cost. The cost is around $20,000. So as today's price, it is 18 to 19 lakhs, both the antenna and the receiver. And you can see the antennas are also quite complex. So there are GNSS OEM boards. They comes in this form. The cost is lower, but one has to know that how to use this one. Actually, the OEM boards are there inside with the other electronics. In this case, the bare electronics is given to you. If you know how to use it, you can write your own software, or you can integrate with readily available softwares. Then OEM boards are quite good for research purpose. We use many OEM boards together with geodetic receivers. Then these are simulators, record and replay system, SDR receivers. They're pretty costly, except the SDR receivers. In case of SDR receivers, one needs to know how to write the software. Here, one needs to know how to use the simulators. The simulators are quite costly. In Indian currency, more than 2 crores, the price may go. So you can very well understand it's not for us, it's for the manufacturers. But this is a good option in between. We call it a record and replay system. It records the scenario and can play back the scenario in your laboratory. It is also not very cheap. It comes around a cost of 24 to 25 lakhs. And there are special purpose receivers for ionospheric monitoring, etc., for timing, for time display and time server. So there are the different types of receivers. Now let us come into the game changes. Since I would say 2000 lasted some 10 years plus, 2015-16, they came into the market. There you can see they're very small, very low cost. So what we call low cost, which is below $100. The antenna cost may vary from $5 to $50. So what is their weight? Less than 100 grams. What are their power consumption? Very low. So you can see they're very small. We call them SWAP-C modules. Size, weight, power, and cost efficient modules. SWAP, small ap, SWAP-C modules like any other electronics. So they are GNSS SWAP-C modules. And these are the antennas. You can very well see. So this one U-Block's Neo M6N, together with antenna you can purchase. Last time when I saw it was 450 rupees. And on the other hand, I was talking about a $20,000 receiver. So, and in many cases, I've seen my students are integrating this type of receivers with different applications, maybe tracking, maybe resource monitoring, this type of thing. Okay, so these are the game changers, and that's why I requested Mukesh sir that let me give the freedom of presenting before you at least 1 or 2 slides on the SWAP-C modules, because so now the SWAP-C GNSS modules, they are single frequency CLS modules or dual frequency modules. So once again, these are the I would say non-exhaustive list. So many companies, including ours, we are bringing into the market because here whatever you are seeing, you have to import. So our company wants to change the scenario. So what we are doing, that we will develop this type of modules in India, so that any education or any research or any real life application developer can use this type of boards directly. They don't have to import. So you can see the cost is $300. So for example, this one is around $300. The antenna cost around $70 to $80, like that. So advantages, they are very small size, multi GNSS they can use, multi frequency they can use. So in SPS they are quite good. They can provide both NME and raw data. They can do port-based measurement and carrier phase-based measurement. They are very power efficient. Generally, they are run directly by connecting with your computer. Your computer through USB supplies its power, and it can run maybe in many cases in fields we have run it for 3-4 hours even. They're RTK enabled, and most importantly, they are low cost. Whenever we are talking about low cost, we are talking about below $1,000, whatever. It should be below 1,000. Below $1,000 we are talking about. And in case of Navic, already in the market, one of the companies, our partner, they have brought into the market Navic L5 plus S modules. So if I want to use S signals also to have the advantages, now it is possible, but the cost is not as low as this type of things, not 300. It will be a bit higher type of module. So those people, those researchers who want to explore the possibilities of using L5 plus S, they can have this one. So what are the different types of Navic hardware which are available in the market? So these are the geodetic receivers, but except this one, these are once again non-exhaustive list. Please do not blame me that you have not shown this company, many others are available. Yes, they are available, but I wanted to give you the feel. Okay, so these are L5 only, but this one is L5 plus S. Simulators and record and replay system, both of them can use Navic L5. This can use Navic case also. Then OEM boards which look like this, timing server and display systems, and most importantly, size, weight, power, and cost efficient modules. So I have given some examples. So this is our board Navitro Luxor. You can see the size, and it is a very low cost Navic L5 receiver. And another newcomer in the sector is the Navic enabled Android smartphones. So I could not, to save time and also number of slides, I could not give the larger size of this one. So you can see, if you look minutely, you can see, so the Indian flag is being shown. So they can track GNSS Navic signals, Navic L5 signal. But word of caution is, none of the mobile phones I repeat, none of the mobile or smartphones or Android phones in the market uses Navic signal for solution. They can track. They will show you, okay, I am tracking. But if you go that, okay, track, give me navigation solution, let long alt using Navic, they cannot do it. So there is a real challenge, and there is an open area for work. Those of you are interested in developing this type of applications. And SWAPC modules, we have shown that they can be used for positioning there, and we found out that it's a paper published in GPS Solutions, that we are comparing the performance of a geodetic receiver with a very $300 very small receivers, and you can see the VTX values are the same. Here also we have shown the S4 values are the same. They can use for time transfer purpose and mass market applications. So when we are talking about mass market applications, so this is the basic idea, that we have got a controller unit which takes geolocation and different types of sensors as per requirement of the user or your client, and it transmits the data over different channel to a central server. So it's a IoT solution in the field, from where the data goes through different channels, and the data is processed here, and ultimately we get the solution in the form of a GIS enabled dashboard or Android app. So on the right hand side you can see, so the data from the hardware, it comes to the central processor, it is processed here. So nowadays, now we are thinking of, and in some small applications we have started using AI for decision making. So it goes to the primary user, it goes to the field level user, it goes to the decision makers. So let me give you two examples. This is one example is NavAgro. We have put this type of modules, navigable devices, electronic device on the field. And here you can see the data directly every 5 seconds, the data is being updated. The soil condition, the temperature, humidity, the pressure, the moisture, the rainfall, the light, everything comes here. And it can be it can be used for prediction of yield, prediction of pest infection, possible pest infection, prediction of possible threat of possible threat of a particular disease for cash crops. So, and also this type of applications helps in reaching the sustainable development goals. So this is one example. This is another example, what we call the nav tramo. So it will be installed on a bus or on a vehicle, and continuously it will transmit its location every predefined interval, maybe 5 seconds or 10 seconds, and on the dashboard we can see where the location is, and we can use judiciously to predict if there is any traffic congestion, if we need any traffic diversion also. That type of algorithm or that type of solutions can be there. So this type of applications can be used for real-time water quality monitoring, disaster monitoring, insurance sector, unmanned and autonomous protection of high security premises where the security has been breached, where we can see that there is some intrusion. So this type of, because we know the geolocation, so where it is being done, at what point of the perimeter. So very easily we can integrate this kind of things. And the future trend is getting, instead of waiting for the future, the very important thing is the spoofing and jamming mitigation, what we call the GIMSE, jamming, interference, meconing, and authentication. So we call it GIMS, spoofing and authentication. It is already implemented, partly implemented in case of Galileo. We need very secure data, so that I can, it's called high accuracy service and authentication service, so that only the authentication signal, not from our enemy's signal, we are getting full. And also getting data from the satellites to get, instead of a terrestrial network, getting data from satellites to very fast PPP or real-time PPP. Already Japan has implemented it, what is called the Madoka. So these are the trends or the very important parameters one should keep in mind. So jamming and spoofing, spoofing, meconing, so and interference. So these are the very important issues. What is a threat to the GNSS community? Also, what already it has been told, that integration of other sensors, for example, inertial navigation system, dead reckoning, and low PNT, low orbit PNT, very near to Earth, say 100, 200 kilometers, multiple satellites are there. So together these technologies move hand in hand, and we will see we can fully exploit the benefits. So this is the further reading. And before I end, so this is our laboratory. So we always try to present it as a case study, that how from an academic laboratory, we rolled out manpower, we rolled out publications, we got recognition, we rolled out manpower who are working in multinational companies and the local companies. We have got national and global footprints. We generated employment, industrial consultancy, collaboration, and more with many agencies. We have some IP rights. We support in national and global training. And finally, we were able to spin off a startup company. Researchers from our laboratory, they are joining to the startup. So the expertise what they have developed over the last couple of years, maybe 6-7 years, it is not I would say it has not it is now being exploited for development of the different hardware and software to the progress of the country. So we are open for, and this is a gift for you. I will copy this link in your chat box. So those of you interested, you can download this 3 posters. It has been developed by us for promotion and education on GNS Navic. So this one tells what is Navic, this one tells how Navic works, and these are the what is the areas and what are the different types of Navic hardware. So you can download the high resolution copy of these 3 posters and get it printed if you like for your students like that. So thank you very much. My sincere thanks to all of you for lending me your ears for more than 1 hour 30 minutes. My thanks to the organizers for letting me share my views and experiences. And last but not the least, all our sponsors, through whose support we could develop our laboratory. So once again, thank you very much. If you have any questions, I will try to okay. So how to stop my presentation? Just one moment. I cannot see the okay, stop sharing. Now, if you have any question, you can ask me. I can spare. If your, I would say, if your energy and patience permits, I can take a few questions. If not, already I have shown that we have got our YouTube channel. In the YouTube channel, most of our lectures on GNSS, they're uploaded there, and also through the coordinators, you can send me the questions. So thank you very much once again.
Thank you, sir. Any questions
Okay.
from the participants? If you're having any questions, please write a mail to
Okay.
sir directly.
Okay. Yes. I'm sharing the drive link. Just one moment. Sorry, I forgot. And if you have any question, you can send it to me. I'll try to answer as fast as possible, or through after the course is completed through Dr. Mukesh. You can send it to me.
Okay. Now I request Rajeshri Madam to present the vote of thanks.
Good evening to one and all. It's an honor and pleasure to deliver the vote of thanks for today's enlightening session. First and foremost, I extend a heartfelt gratitude to your esteemed speaker, Dr. Anindya Bose. Your knowledge sharing today has been truly commendable, sir. The way you combined your seniors' expertise, years of experience, and practical insights made the entire session both engaging and enriching. Even the latest trends regarding that security and Navi hardware which is available, really that is given us a very enlightening session. and you have given us new directions to think about, fresh perspectives to apply in our academic and professional journeys. We are deeply grateful for the time and effort you dedicated to being with us and for inspiring us with your thoughtful presentation. We are also thankful to our secretary sir and our principal sir and dean R&D and HOD ma'am, organizing team, and to every one of the uh, staff members who have been involved in organizing such a wonderful thing. And really, I must thank to the participants. Even at the night time, they are ready to listen. And moreover, sir has been ready to clear all your doubts, even in spite of his 9 o'clock, and he has taken 1.5 hours without any interruption. He has given a very good, very, very, very commendable one. You, sir, has given. Really thankful, sir. Really, really, it is an enlightening session. Thank you, sir. Thank you very much.
Okay, thank you very much, madam. Thank you very much, Mukesh sir, and all the participants. So once again, if you have any question, I'd be very happy to try to answer the questions. I cannot say I can answer all the questions. I'll try to answer those questions. Okay, thank you very much.
Thank you, sir. Very
Thank
kind
you,
of you, sir. Thank you, sir.
Okay, bye bye.
We will conclude the session, sir. Thank you.
Okay, thank you very much.
Thank you, sir. Participants, please fill the feedback session link